Welcome to the course. This introductory chapter establishes the strategic framework for the Meraki Solution Specialist examination by covering our architectural foundation and course navigation. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to Cisco Systems Inc. in any way. All trademarks, including Cisco and Meraki, belong to their respective owners. This content is for informational and educational purposes only and is intended to assist in exam preparation. It does not guarantee certification or official product support. If you are aiming to validate your expertise in the Cisco Meraki ecosystem, you have come to the right place. This course is meticulously designed to mirror the actual exam blueprint, ensuring you are not just memorizing answers, but truly understanding the underlying mechanics of cloud-based network management. We will move through every critical domain, from wireless RF tuning and SD-WAN steering to endpoint management and smart sensor integration. By the end of this journey, you will possess the practical technical knowledge required for the industry standard certification and, more importantly, the competence to manage complex enterprise deployments with confidence. The core of everything we do in a Meraki environment relies on the unified cloud architecture, which represents a significant departure from traditional legacy management styles. Unlike classic models where you manage individual nodes directly, the Meraki cloud acts as a centralized controller that keeps your configuration state in sync across geographically dispersed locations. A critical concept here is out-of-band management, which separates the management control plane from the actual user data plane. Because the data packets flowing through your switches and access points never traverse the cloud controller, you gain both performance efficiency and a robust security posture. Even if a site loses its connection to the internet, the local hardware continues to forward traffic based on the last known configuration. This decoupling is precisely what makes the Meraki solution scalable for enterprise organizations that require high availability and simplified administrative oversight. Successfully navigating the Meraki dashboard is a skill that will save you countless hours during both the certification exam and your daily operational tasks. Think of the dashboard as your single pane of glass, where the hierarchy starts at the organization level and drills down into specific networks and individual devices. You will learn to effectively parse critical telemetry data, such as per-client bandwidth usage or event logs that reveal connectivity issues before they turn into major support tickets. We will practice how to use tags and search filters to isolate data in multi-tenant environments, which is a common requirement in large-scale deployments. Understanding where to locate configuration settings versus monitoring metrics is key. For example, knowing that device status is found under the Monitor tab, while security policies live within the Configure tab, is foundational. By mastering this navigation, you will be able to perform rapid troubleshooting and ensure your deployments meet the specific performance requirements outlined in the exam objectives. Beyond the technical interface, this course covers the operational essentials of licensing, multi-organization design, and role-based access control. Licensing in the Meraki world is tied to the hardware and the specific services enabled, and misunderstanding these models can lead to service interruptions or compliance issues. We will break down how to map your network requirements to the appropriate licensing tier, ensuring that your architecture is both cost-effective and fully supported. Our discussions on role-based access control will focus on how to maintain the principle of least privilege, allowing you to delegate administrative tasks without compromising the integrity of your global network policies. We will also examine how to structure your dashboard organization to facilitate smooth growth as your footprint expands across different regions and business units. Establishing this organizational rigor early on is exactly what separates a haphazard implementation from a professional-grade, enterprise-ready infrastructure. I look forward to our next session together. Welcome to our exploration of Meraki Cloud Architecture, where we will examine the technical foundations of the out-of-band management model. In this chapter, we will master the mechanics of secure cloud-based control that separate management traffic from actual data flows. The fundamental design of the Meraki platform relies on a strict out-of-band management model that differentiates it significantly from traditional on-premise controller architectures. While conventional setups often require every packet of user traffic to traverse a centralized controller, Meraki hardware operates by keeping all user data local to the physical network fabric. This means that if you are transferring a file between two devices on the same local area network, that traffic never leaves your building. Instead, the management plane acts as a control layer that exists entirely apart from the user data path. Configuration changes, monitoring metrics, and health telemetry are sent to the Meraki cloud via dedicated encrypted tunnels. By segregating these concerns, the architecture ensures that a disruption in cloud connectivity does not result in a spontaneous cessation of network services. Users remain connected to the internet and internal resources regardless of the state of the connection between the hardware and the global management dashboards. Communication between edge devices and the global data centers is maintained through persistent, proprietary tunnels. These tunnels are established using TLS to ensure that all information transmitted over the internet remains confidential and securely associated with the specific organization. If a device experiences a temporary loss of connectivity to the management plane, it enters a localized buffering state. During this time, the device continues to function using its last known good configuration, which is stored in local volatile and non-volatile memory. This design choice is critical for enterprise resiliency, as it prevents the network from collapsing during provider outages. Once the connectivity to the cloud is restored, the device synchronizes its state, uploading accumulated telemetry data and downloading any pending configuration updates that were pushed by administrators during the downtime. This robust heartbeat mechanism ensures that the cloud management platform maintains an accurate representation of the network state without requiring constant, uninterrupted bidirectional communication. Redundancy is built directly into the cloud infrastructure to guarantee high availability for administrative operations. Meraki utilizes geographically dispersed data centers to host the dashboard and configuration services, ensuring that failover mechanisms are triggered automatically should a primary site become unreachable. This strategy extends to the back-end databases and processing tiers that handle the massive volume of telemetry data generated by global deployments. The platform also employs strict privacy controls to ensure that the data being collected does not violate regulatory compliance standards. Telemetry is purely operational, focusing on device health, traffic statistics, and interface status, rather than the content of the packets traversing the user data plane. For organizations subject to stringent requirements like GDPR or HIPAA, this separation of management telemetry from sensitive user traffic serves as a primary architectural defense against potential data breaches. Transitioning from traditional on-premise controller designs to this agile cloud model offers significant operational advantages for scaling enterprise infrastructure. In legacy environments, updating firmware or rolling out new policies often involved manually upgrading physical controllers and dealing with the risk of synchronization drifts between different sites. Conversely, the Meraki approach leverages a globally unified firmware staging pipeline that enables automated scheduled updates across entire organizations. Performance optimization is similarly improved, as the cloud platform can correlate data from thousands of devices to identify trends and suggest configuration adjustments. This continuous pipeline architecture allows IT teams to manage massive networks with the same simplicity as an individual small branch office. By centralizing the control plane while decentralizing the data plane, administrators regain time previously spent on maintenance, redirecting those efforts toward optimizing network throughput and security posture. We'll see you in the next lecture. Welcome back. This chapter focuses on mastering the Meraki dashboard, the singular interface for managing your entire global infrastructure. In this series, you will learn to navigate the complexities of Meraki's single pane of glass management system. We will dissect the architectural hierarchy, moving from organizations down to granular configuration tags, which is essential for scaling operations. By the end of this journey, you will possess the skills to manage massive, multi-site deployments with professional efficiency. Investing your time here is the single best way to reduce your operational overhead and ensure network consistency. Let us begin by demystifying the structure of the dashboard itself to prepare you for the certification exam. The Meraki dashboard is structured as a hierarchical tree, starting at the organization level, which serves as the top-level container for all Meraki resources. Beneath the organization, you manage individual networks, which are logical groupings of devices that share common configuration settings and policies. When you log in, the global search bar becomes your primary tool for navigating through thousands of endpoints, allowing you to jump instantly to a specific device, client, or configuration page. It is vital to recognize that your permissions are inherited from the organization down to the network level, meaning your administrative rights dictate exactly which dashboard features are visible to you. Configuring your user-specific preferences such as time zones and alert thresholds ensures that the dashboard reflects the operational reality of your specific regional responsibilities. We also utilize configuration tags to apply settings across disparate networks, which acts as a powerful abstraction layer for managing large-scale global deployments without manual repetition. Proficiency in this navigation is not just a convenience, but a necessary discipline for maintaining control in environments where thousands of devices are deployed across diverse geographic locations. Managing inventory within the dashboard requires a clear understanding of the allocation model, where hardware is claimed into an organization and subsequently assigned to specific networks. When you navigate to the inventory section, you're essentially looking at the pool of available hardware that has not yet been bound to a function or a site. The real-time health badges presented on the main overview screens provide an immediate pulse check, utilizing color-coded status indicators to highlight connectivity issues or licensing expirations. Once you drill down into a network, the topology map serves as the visual representation of your Layer 2 and Layer 3 connections, allowing you to trace physical hardware dependencies instantly. This map dynamically updates based on LLDP and CDP data, providing an accurate view of how devices are daisy-chained or connected to core switches. If you encounter a localized network issue, these visual tools allow you to bypass the need for physical console cables by showing you exactly which port on which switch is the potential point of failure. By auditing these active hardware lists against your internal documentation, you establish a clear governance baseline that prevents configuration drift in complex, multi-site setups. Optimizing your administrative view is key when you are operating in environments with significant geographic distribution and high device density. You should prioritize the use of the dashboard's tagging system to filter your views, which allows you to segment your focus by location, building, or service type. When you select a specific tag, the dashboard effectively hides the noise of irrelevant hardware, surfacing only the devices that matter to your current troubleshooting goal. This granular control is further enhanced by the ability to customize your sidebar and dashboard widgets, letting you place the most critical performance metrics front and center. Effective troubleshooting relies on the efficient fusion of these logical groupings and the physical state of your distributed endpoints, which we verify through constant monitoring. As you become more comfortable with these workflows, you will find that the time to resolution for common network incidents drops significantly because you are no longer searching for the right view. This is the foundation of high-level network management, where the tool itself handles the complexity, leaving you to focus on the policy and performance of the infrastructure. I will see you in the next lecture. Hello, and welcome back to our deep dive into the Meraki ecosystem. In this section, we will explore the critical architectural decisions required to build a scalable and maintainable organizational structure within the Meraki dashboard. Designing an effective organization hierarchy is the foundation upon which every other configuration rests. When you first approach a Meraki deployment, the temptation is often to group everything under a single organization to simplify initial access. However, this monolith approach often becomes a liability as the business grows, introduces multi-tenant requirements, or necessitates strict administrative boundary separation. We must carefully evaluate whether to implement a consolidated structure or split entities into separate, distinct organizations. A single organization container provides global visibility and a unified view, which is excellent for centralized monitoring, but it lacks the granular separation required for security auditing or per-tenant billing models. Conversely, managing multiple organizations creates effective silos, but introduces operational overhead, as you must navigate between different dashboard views frequently. Successful design relies on identifying your administrative boundaries first before you add a single device to the inventory. Once you decide on the organization containers, the next layer of complexity is managing the logical boundaries within those containers through networks. Networks in Meraki serve as the fundamental grouping mechanism for hardware, and they act as the scope for configuration inheritance. By structuring your networks with care, you can leverage configuration templates to mass deploy settings across hundreds of sites simultaneously. This is where many administrators encounter issues. They create networks that are too specific, leading to thousands of unique configurations that are impossible to maintain at scale. Instead, you should group your physical locations into cohesive logical networks based on common functional characteristics rather than just geography. If 10 retail stores share the same security posture, VLAN structure, and SSIDs, they should all be anchored to a single configuration template. This approach ensures that when you push a firewall policy change, it propagates consistently across the entire fleet without the risk of accidental drift. Configuration templates represent a powerful abstraction for achieving consistency across your environment, but they must be implemented with a disciplined approach to avoid overlapping conflicts. When you apply a template to a network, the network inherits all settings defined in the parent object. If you find yourself in a situation where a specific site requires a deviation from the global norm, relying on manual overrides is a poor design choice that will inevitably compromise your audit integrity. Instead, you should utilize target network bindings to apply subsets of configurations to specific device models or switch profiles within that template. This enables a clean inheritance chain where you can maintain a base configuration for an entire enterprise while safely overlaying unique, site-specific requirements. By keeping the hierarchy shallow and the inheritance rules explicit, you ensure that your provisioning workflows remain fast and predictable even as your footprint grows into thousands of managed units. Beyond templates, the use of tagging serves as your primary tool for filtering and orchestration within the dashboard. A well-considered tagging strategy is not just for convenience. It is a vital mechanism for automating group actions and API queries. You should define a naming convention early in your design phase that categorizes devices, networks, and clients based on metadata rather than transient properties. For instance, tags should reflect roles, environments, or deployment phases, such as branch type or production status. When you combine consistently applied tags with the dashboard API, you move from manual intervention to automated orchestration, where you can query for all switches with a specific tag to perform bulk upgrades or policy updates. This discipline transforms your dashboard from a static configuration portal into a dynamic, programmable infrastructure that grows alongside your organization without increasing your manual administrative burden. As you scale, always prioritize the separation of concerns between your identity management and your physical resource grouping. While physical switches and access points reside in specific sites, your management access, the ability to configure those devices, should be governed by a role-based access control policy that is independent of the network grouping. By decoupling these layers, you maintain the agility to rearrange site responsibilities or integrate new business units without tearing down your core configuration templates. Designing for longevity means accepting that requirements today may only be a fraction of what they will be in 2 years. By enforcing strict boundaries, leveraging template inheritance, and maintaining a robust tagging strategy, you create a system that is resilient to change. See you in the next lecture. Welcome to the chapter on access management, where we define how you retain absolute control over your Meraki environment while distributing administrative duties effectively. We will focus on implementing secure, role-based policies and authentication methods to protect your infrastructure. In this chapter, we will master the art of restricting administrative access to ensure that users have only the permissions necessary to perform their roles. You will learn to construct minimal privilege security postures, effectively isolating local branch administrators from sensitive core backend configurations. By the end of this module, you will understand how to integrate external identity providers and enforce strict authentication, which is vital for any professional deployment. This knowledge is not just about passing an exam, but about building a defensible architecture that prevents internal vulnerabilities and unauthorized changes. Choosing this path ensures you gain the practical skills required to manage enterprise-grade networks with professional-level security standards. Effective access control begins with a clear understanding of the organization structure and how administrators are assigned to it. Within the Meraki Cloud Portal, you have the ability to define distinct roles that transcend the basic full administrator toggle, allowing you to tailor specific permissions based on functional needs. You might need to grant a network technician the ability to check port status or power cycle a switch without allowing them to modify the overarching firewall rules or change the organization's SSO configurations. This involves navigating to the Administrative Accounts section and selecting an appropriate privilege level for each user, which can range from read-only access for auditing purposes to full read-write capabilities for network configuration. By partitioning responsibilities, you minimize the blast radius of any potential human error, ensuring that specialized staff cannot inadvertently alter global network policies. It is a fundamental principle of security, similar to how we isolate dependencies in software development to keep systems resilient and maintainable. When scaling your administrative team, manual account management quickly becomes unsustainable and a potential security risk in itself. This is where Security Assertion Markup Language, or SAML, becomes an essential tool for centralized authentication. By integrating your existing identity provider, such as Microsoft Entra ID or Okta, you shift the burden of lifecycle management and password policy enforcement to a system specifically designed for that purpose. During the configuration process, you define attributes that map groups from your identity provider to specific Meraki dashboard roles, effectively automating the onboarding and offboarding process for your IT staff. This ensures that when a user leaves the organization or changes departments, their access to the Meraki dashboard is revoked or adjusted automatically without manual intervention. The integration requires careful exchange of metadata between the identity provider and the Meraki cloud, confirming that the handshake is secure and that authentication remains private. Beyond identity integration, enforcing multi-factor authentication is no longer optional for maintaining a secure environment. Meraki provides the capability to mandate MFA for all administrators, adding a layer of security that protects against compromised credentials. Even if an attacker gains the password for an administrative account, they are stopped at the second factor, provided the mobile authentication token is handled correctly. Furthermore, security auditing is bolstered by the comprehensive modification logs available within the dashboard's change history. Every significant alteration to a policy, rule, or configuration is time-stamped and attributed to the specific user account that initiated it. This visibility allows administrators to troubleshoot unexpected network behavior by tracing it back to a specific set of changes. It also serves as a critical governance feature, as you can generate reports that demonstrate compliance with security policies during internal or third-party audits. Finally, we must address the programmatic access required for automated network orchestration and monitoring. The Meraki dashboard provides a robust API that allows you to interact with the back-end infrastructure, but this power must be handled with care. Generating API access tokens is a sensitive operation, and you should always follow the principle of least privilege by creating specific, scoped keys for third-party service providers or internal automation scripts. If a service only needs to fetch telemetry data, do not provide it with write access to your firewall or routing tables. We also see organizations integrating their local radius or Active Directory environments for network service authentication, which fits into the broader theme of keeping authenticated access consistent across the entire technology stack. By mastering these patterns, you bridge the gap between simple dashboard usage and a mature, professional-grade operational model that keeps your network resilient. See you in the next lecture. Welcome back. In this session, we will explore the critical mechanics of the Cisco Meraki licensing architecture. Understanding these models is essential for maintaining network continuity and operational compliance within the dashboard environment. Meraki operates on a subscription-based model, which fundamentally differs from traditional perpetual software entitlements in the enterprise networking space. The two primary structures you need to differentiate are the co-termination model and the recently introduced per-device licensing framework, which exists to satisfy more granular hardware lifecycle requirements. In the co-termination model, all licenses within a single organization are aggregated to a common expiration date, simplifying renewal management by unifying the platform's support and feature entitlements. When you add a new device to an organization using co-termination, the system automatically calculates the remaining time and adjusts the organization-wide expiration date accordingly, based on the value of the license. Conversely, per-device licensing assigns specific license entitlements to individual hardware serial numbers, providing a more rigid but transparent mapping of service contracts to physical assets. This flexibility allows administrators to maintain distinct renewal dates for geographically dispersed networks or unique hardware tiers, which is particularly beneficial for organizations with disparate technology refresh cycles. You must be careful when transitioning between these models because the migration process is generally a one-way operation that cannot be easily reversed once applied to an organization. Effective management of these licenses requires a clear understanding of the grace period and the consequences of exceeding license compliance. When a license expires, the Cisco Meraki dashboard does not immediately trigger an outage, but instead grants a 30-day grace period during which the network remains fully functional. During this interval, it is your responsibility to redeem new license keys or correct entitlement imbalances to avoid reaching an invalid license state. Once that period expires, the dashboard will display persistent warnings, and if the situation remains unresolved, administrators may eventually lose the ability to modify configurations or push firmware updates to the equipment. It is important to note that the data plane generally continues to forward traffic even if the management plane becomes restricted due to compliance errors. However, relying on this behavior is an unsustainable operational strategy that introduces significant risk to network availability and security. Proactive monitoring of the license status page should be a formal part of your monthly administrative duties to ensure that alerts do not escalate to the point of service degradation. Complexities often arise when moving hardware between dashboard organizations or upgrading technology tiers, such as moving from a base switch to an advanced security appliance. When you transfer a device from one organization to another, the license must either follow the device or be re-provisioned to match the destination organization's licensing model. In a co-termination organization, moving a device consumes the remaining credit to adjust the new organization's total expiration date, which can lead to unexpected shifts in your renewal calendar. Conversely, under per-device licensing, the entitlement must be unassigned from the original serial number and correctly redeemed against the new piece of hardware to reflect the correct feature tier. You must ensure that the license tier matches the hardware capability, such as ensuring that an advanced security license is active if you intend to utilize Layer 7 traffic shaping or specific threat protection features. Calculation logic relies on the total number of days and the count of each hardware type, meaning that inconsistent license applications can lead to confusing administrative overhead. When auditing your infrastructure, always verify that the serial number of every active node is accounted for within your current inventory to prevent unauthorized usage status. See you at our next session. Welcome back. Today we are starting a new chapter focused on deployment workflows. We will explore how to transition enterprise hardware from procurement to production using optimized zero-touch provisioning methodologies. The foundation of any successful Meraki deployment lies in the effective management of the centralized inventory bank. Before a single device is shipped to a remote location, it must be claimed into the Meraki organization using its serial number or an order identifier. This initial step transforms a physical asset into a logical entity that you can manipulate within the dashboard. Once claimed, the hardware exists in the general inventory pool, waiting to be assigned to a specific target network. By pre-staging these assignments, you essentially map the device to its final destination before it even leaves your warehouse or distributor. This decoupling of procurement from physical installation allows your logistics team to handle the heavy lifting while you focus on the logical architecture of the network. Proper inventory management prevents the common pitfalls of orphaned hardware and ensures that policies are correctly cached in the cloud long before the device performs its first check-in. Pre-staging configurations represent the core of the zero-touch experience, as they allow you to define settings for an appliance that isn't yet physically connected to the internet. You can configure virtual interfaces, security policies, and even cellular provisioning parameters within the dashboard while the hardware is still in transit. When the appliance eventually powers on, it attempts to contact the Meraki cloud via a secure heartbeat over HTTPS. If you have already established a target network and applied the appropriate settings, the device will automatically pull this configuration upon reaching a ready state. This process is highly dependent on the device knowing where to look for instructions, which is managed by the Meraki cloud registration process. Even in scenarios where cellular uplinks are required, the firmware handles the dynamic IP assignment or static address implementation provided you have predefined these variables. By minimizing the number of manual steps required on site, you drastically reduce the risk of human error during the critical power-on sequence. Understanding the device boot state is essential when you find yourself troubleshooting a deployment that refuses to come online. When an appliance first receives power, it will cycle through a boot process where it checks its local status page for existing configuration or attempts to reach the cloud gateway. If the uplink environment provides a valid IP address via DHCP, the device will typically attempt to reach the registration servers to initiate its phone home heartbeat. If your network environment requires a static IP, you may need to utilize the local status configuration page to enter these details manually before any automated cloud registration can take place. Once the device establishes connectivity and validates its serial number against the assigned network, it will pull the latest firmware and policy set concurrently. This lifecycle is remarkably consistent, making it predictable enough to build comprehensive deployment playbooks for nationwide rollouts. By standardizing this approach, you eliminate the need for highly skilled technicians at every remote site, thereby accelerating your overall project timeline significantly. I look forward to discussing the specifics of wireless deployments in our following session. Welcome back. We are going to explore the critical aspects of physical access point placement to ensure optimal wireless performance. This session will ground your understanding of how physical realities dictate the success of any high-density Meraki MR deployment. When we approach the challenge of placing Meraki access points, we must move beyond the naive assumption that coverage equates to capacity. High-density environments demand that we treat radio frequency propagation as a finite resource, where the physical medium, such as concrete walls or glass partitions, actively modulates the reach and scattering of our signals. Understanding the attenuation characteristics of these materials is the first step in ensuring that our coverage modeling actually matches the reality of the floor plan. If we fail to account for how a drywall partition absorbs signal versus how a metal-framed cubicle reflects it, we invite the hidden node problem into our network, which effectively cripples throughput. Every design decision you make regarding placement should be validated against the projection of user density rather than just an arbitrary count of square footage. A dense lecture hall requires a fundamentally different mounting strategy than an open office layout, particularly when we aim to minimize co-channel interference. Physical mounting considerations are equally important when we consider the mechanics of spatial streams and antenna gain. Meraki MR access points often utilize sophisticated antenna arrays that expect a specific orientation, usually ceiling-mounted and horizontal, to distribute the wireless footprint as intended. When we deviate from these manufacturer guidelines by mounting devices on walls or inside metal enclosures, we distort the radiation pattern and degrade the effectiveness of MIMO, or multiple input, multiple output technology. Furthermore, we must carefully consider our power over Ethernet budget, especially as we scale up to multi-gigabit uplinks that require higher power parity levels. An underestimated PoE budget leads to scenarios where the access point throttles its radio capabilities or disables certain spatial streams to remain operational, which is a silent killer of system capacity. Always ensure that the upstream switching infrastructure can provide the necessary wattage to meet the demands of the AP when all radios and streams are firing under load. Maximizing system capacity also requires a deliberate approach to channel width selection, which is a classic trade-off between individual client throughput and total aggregate airtime. While wide channels might look impressive in a lab environment, they often result in massive amounts of co-channel interference in deployed office spaces where spectrum is crowded. By narrowing your channel width, you create more non-overlapping channels, allowing you to increase the overall count of access points without having them fight each other for the same slice of the airwaves. This strategy of frequency reuse is fundamental to preventing the early capacity exhaustion that plagues poorly planned wireless networks. It is far more effective to have a higher density of access points configured correctly with narrow channel widths than to have a few APs running wide channels at high power. Remember that wireless design is an exercise in management of the shared medium, and your physical placement is the foundational layer upon which every other configuration, like RF tuning, sits. See you in the next lecture. Welcome to our deep dive into SSID settings, where we will examine the mechanics of wireless configuration within the Meraki dashboard. We will explore how to transition from basic connectivity to robust, enterprise-grade network segmentation. When we approach SSID configuration, we have to look past the basic toggle switches and consider the architectural implications of our choices. An SSID is not merely a broadcast name. It is a logical entry point into your network that necessitates a well-defined security and traffic policy. You must decide whether your client should exist on the same subnet as your wired infrastructure or if they require a separated, tunneled path. Native bridging acts as the default behavior, where the access point acts as a transparent layer 2 bridge, passing traffic directly onto the switch port. This approach relies on your upstream infrastructure for DHCP and gateway services, which effectively keeps your wireless traffic pattern clean and predictable. However, when you introduce complex authentication requirements, such as WPA3 enterprise encryption or 802.1x via an external radius server, the management of that traffic becomes significantly more nuanced. You are tasked with defining exactly how that traffic enters the network and what permissions those clients hold the moment they authenticate. Authentication is the bedrock of a secure wireless strategy, and the Meraki dashboard offers granular control over these mechanisms. For corporate environments, 802.1x is the standard, allowing you to interface with infrastructure like Cisco ISE or a local free radius server. When configuring these paths, you must pay attention to how radius attribute mappings allow for dynamic VLAN assignment. This feature is particularly powerful because it enables the network to place a user into a specific segment based on their credentials rather than the physical location of the access point. For instance, a user in the finance department might be dynamically assigned to VLAN 20, regardless of which physical AP they associate with in the building. This abstraction requires your infrastructure to be ready to handle multiple VLAN tags at the wireless boundary, which means your trunk ports must be configured to pass all relevant traffic. Missteps here often stem from a mismatch between the radius response and the configured VLAN IDs on the switch, so verification is non-negotiable. Beyond mere authentication, you often need to consider the needs of varied device types, including unmanaged assets and untrusted IoT components. This is where client isolation and custom access control filters become essential defensive layers within your wireless architecture. Client isolation creates a micro-segmentation effect by preventing devices on the same SSID from communicating directly with one another, which is a critical feature when you cannot guarantee the security posture of an endpoint. You can further refine this by implementing Layer 3 firewall rules directly at the access point, effectively dropping unauthorized traffic before it ever hits your upstream gateway. By leveraging these boundary controls, you treat the access point as a first-line enforcement node. These policies should be applied with precision, as overly restrictive rules can break application functionality while overly permissive ones introduce unnecessary risk. Consistency across your deployment is key, and the Meraki dashboard allows you to propagate these security policies across organizational groups to ensure a uniform posture. Finally, we must consider the trade-offs between local switching and central VPN routing when designing for roaming users. When you need to maintain a single session across an entire campus, particularly when that campus is geographically dispersed, simple bridging may prove insufficient. Central VPN routing allows you to tunnel traffic from the access point back to a Meraki security appliance, which essentially anchors the user to a central gateway regardless of their physical location. This is an elegant solution for maintaining consistent IP addressing and security policies, but it comes at the cost of additional latency and secondary load on your security appliance. You have to evaluate whether your applications are sensitive to the increased round-trip time associated with this backhauling approach. Conversely, Meraki DHCP bridging offers a middle ground by allowing the AP to lease addresses in a way that limits broadcast traffic while maintaining a local path. Choosing between these architectures requires a clear understanding of your traffic patterns and your acceptable threshold for latency in a mobile environment. I will see you in the next lecture. Welcome back. In this chapter, we explore how Meraki Auto RF technologies and radio profiles function to dynamically optimize your wireless infrastructure. Wireless environments are inherently unpredictable because the radio frequency spectrum is a shared resource subject to constant change. In a corporate environment, interference can arise from neighboring access points, non-Wi-Fi devices like microwaves or motion sensors, and simple architectural obstructions. Meraki addresses this variability through Auto RF, a suite of technologies designed to continuously monitor your local spectrum conditions without manual intervention. By analyzing the background noise, signal-to-interference ratios, and channel utilization, these access points make real-time decisions about transmission power levels and channel assignments. The primary objective is to maintain a predictable cell size while ensuring that co-channel interference is kept to an absolute minimum. When an access point identifies a degradation in quality, it does not merely wait for an administrator, it proactively shifts its radio configuration to recover performance. This self-healing architecture is essential for modern high-density deployments where the manual configuration of hundreds of radios would be logically impossible. The foundation of this automated intelligence is the Meraki cloud, which aggregates telemetry data from every access point to build a comprehensive map of the radio environment. Unlike legacy systems that rely on static, manually assigned radio parameters, our approach leverages the collective observation of the entire network. When you implement a radio profile, you are essentially setting the boundaries within which the automated engine is allowed to operate. You might define specific channel selection pools to avoid overlapping with legacy devices that cannot operate on DFS channels, or restrict maximum channel widths if you prioritize stability over raw throughput. By constraining the automated engine via these profiles, you ensure that the system does not make decisions that conflict with your specific physical environment or regulatory requirements. This balance between cloud-based intelligence and administrator-defined guardrails allows the network to adapt to interference patterns that emerge and vanish throughout the business day. Management of legacy handoff clients remains a challenge in many enterprise networks, necessitating the careful adjustment of data rates. If you allow a device to transmit at the lowest possible data rate, it will consume a disproportionate amount of airtime, effectively slowing down every other client connected to that radio. Within the radio profile, you can exclude lower data rates, forcing clients to connect at a higher efficiency or disconnect earlier as they roam away from an access point. This mechanism ensures that your roaming logic is aggressive enough to facilitate a seamless transition to a stronger signal before the current connection quality drops below an acceptable threshold. By trimming the excess tail of the coverage area, you create smaller, more efficient cells that prevent sticky clients from dragging down the performance of the entire floor. Properly configuring these excluded rates is perhaps the most direct way to translate engineering theory into a quantifiable increase in user satisfaction. When we consider the movement of people and devices through complex multi-floor spaces, the importance of transmission power management becomes clear. If an access point transmits at maximum power, it may inadvertently reach clients on different floors, creating unnecessary interference that complicates the client's roaming decision. Auto RF dynamically lowers the transmission power of access points when it detects sufficient signal overlap, which reduces the contention domain and improves the overall signal-to-noise ratio. This constant state of flux requires a system that can distinguish between a temporary spike in channel utilization and a long-term shift in the environmental topology. Meraki handles this by employing weighted averages to determine if a channel or power change is truly beneficial before triggering an update. This level of sophistication provides a robust, low-maintenance wireless architecture that scales linearly regardless of whether you are managing a single office or a global campus. I look forward to our next session together. Welcome to our session on guest networks, where we will examine how to build secure and scalable wireless access for visitors while maintaining the integrity of your internal infrastructure. When designing a guest network within the Meraki ecosystem, your primary objective is to create a logical and physical separation between untrusted public traffic and sensitive corporate resources. This is achieved most effectively by utilizing isolated guest VLANs, which ensure that guest traffic does not bleed into your internal subnets at the Layer 2 or Layer 3 level. By assigning a specific VLAN ID to the guest SSID, you create a dedicated pathway for internet-bound traffic that bypasses internal gateways. Beyond simple VLAN tagging, you must implement local firewall isolation settings within the Meraki dashboard to explicitly deny traffic from the guest subnet to any internal IP ranges. This secondary layer of protection is essential because it prevents curious or malicious users on the guest network from attempting to probe your printers, internal servers, or management interfaces on the wired infrastructure. Once the network isolation is solidified, the focus shifts to how the user interacts with the guest portal through splash pages and authentication workflows. Meraki allows for highly customized splash pages, which can include corporate branding and explicit terms of service click-through agreements that satisfy legal requirements for public internet exposure. You might also consider integrating third-party credential authentication or social media login plugins, which turn a simple connection attempt into a structured onboarding process. For more regulated environments, implementing SMS-based registration ensures that a valid mobile number is associated with the session, providing a layer of accountability for the guest user. Integrating a native billing engine can further complicate or monetize this access, offering time-limited or data-limited passes that are managed automatically by the cloud platform without manual intervention from your IT staff. Managing the impact of these users on your overall bandwidth availability requires the configuration of custom throughput limits, or what we refer to as bandwidth throttling profiles. By applying granular rate limits to the guest SSID, you prevent a surge in guest activity from degrading the performance of mission-critical applications on the internal network. You can set these policies to be either per client or per network, allowing for dynamic allocation of resources during peak utilization hours without needing to reconfigure individual access points. Furthermore, you might utilize bypass scheduling rules to grant specific devices or users permanent access without landing page friction, maintaining a balance between security and user convenience. These settings ensure that your guest architecture remains performant, predictable, and resilient against consumption spikes that would otherwise threaten your production environment. Finally, the Meraki dashboard provides valuable visibility into this segregated traffic through its built-in reporting and analytics features. Even though the guest network is fully isolated, the infrastructure continues to gather statistical usage data that informs your capacity planning and helps you track seasonal trends in visitor behavior. This telemetry is presented in a way that respects the logical separation of the networks while giving engineers the necessary diagnostic information to troubleshoot connectivity issues. When you maintain a strict separation between public web access and private systems, you minimize the attack surface of your organization while still providing a professional, frictionless experience for guests. Mastery of these settings allows you to transition from a simple open network to a sophisticated, secure access model that fulfills all enterprise requirements. I will see you in the next lecture. Welcome back to this exploration of Meraki wireless concepts. We are beginning our section on wireless security, where we will focus specifically on the advanced threat mitigation provided by Air Marshal. In an enterprise environment, the perimeter is not merely defined by the physical walls of your building, but by the reaches of your radio frequency spectrum. Air Marshal is the dedicated wireless intrusion detection and prevention system integrated directly into the Meraki ecosystem, designed to monitor the airwaves for any anomaly that might compromise your network integrity. We will examine how this system functions by scanning for unauthorized access points, which we refer to as rogues, and evaluating the threat posture of the environment. Unlike traditional systems that might require overlay hardware, the Meraki architecture leverages the existing access point radios to continuously listen for traffic, effectively turning your infrastructure into a distributed sensor network. Our focus here is on the mechanics of detection and the subsequent automated responses that keep your data traffic secure from external radio frequency exploitation. The foundation of any robust security strategy begins with correctly defining what constitutes a threat. Within the Meraki dashboard, we configure detection rules that allow the system to differentiate between an actual rogue access point and, for instance, a neighboring business's wireless signal or a nearby cellular hotspot. It is essential to understand that simply seeing another signal does not necessarily mean it represents a malicious intent, as many devices interact with the spectrum in benign ways. By setting appropriate parameters, we minimize false positives that could lead to unnecessary containment efforts and potential administrative friction. You must carefully define the SSID profiles and hardware signatures that trigger a security alert, ensuring that our containment mechanisms only activate when a genuine deviation from our security policy is observed. Once a device is identified as a threat, Air Marshal can be configured to take automated action through a process known as containment. This action, often referred to as wireside or radio-side containment, attempts to prevent users from associating with the malicious device. Radio-side containment works by sending 802.11 deauthentication frames to any client attempting to connect to the identified rogue access point, effectively disrupting the connection between the user and the unauthorized hardware. From a design perspective, this is a powerful yet aggressive capability that requires careful scheduling and policy definitions to ensure it does not accidentally interfere with legitimate, mission-critical infrastructure and surrounding environments. We need to be aware of the regulatory and operational risks here, as disrupting unauthorized networks carries implications that extend beyond our own physical property lines. Mitigation extends beyond just rogue detection to include the active defense against packet floods and sophisticated deauthentication attacks. When an attacker attempts to flood the network with management frames or force clients to disconnect, the Meraki APs detect the unusual spike in management traffic patterns. Automating the response to these events allows the network to maintain its stability even during active interferences. We will discuss how to tune the sensitivity of these scanning radios to balance between visibility and the performance impact on the serving functions of the access points. By mastering these containment scheduling parameters, you create a responsive boundary that can adapt to changing conditions in the spectrum without constant manual oversight from the network operations team. Finally, we must integrate these capabilities into a broader workflow that includes remediation and auditing of security events. Effective management of a secure network requires that we treat air-marshaled data as a primary source of truth for physical security audits. When the system flags an event, it logs the time, the physical location, and the perceived severity, providing the context required to investigate potential physical breaches. We must also consider the false positive remediation workflows, which allow network administrators to whitelist known friendly devices, ensuring that our automated defenses do not become a nuisance. Through this methodical approach to spectrum management, you ensure that your wireless deployment remains a secure and reliable access layer for your enterprise, effectively insulating it from the typical vulnerabilities associated with open radio environments. Talk to you in the next lesson. Welcome to our exploration of location analytics within the Meraki ecosystem. In this chapter, we will master how to extract meaningful spatial intelligence from your existing wireless infrastructure to drive data-informed business decisions. Meraki access points function as sophisticated sensor arrays that go well beyond simple connectivity by monitoring the radio frequency environment. Every wireless device that has Wi-Fi enabled periodically broadcasts probe requests as it scans for known networks, even if it is not actively associated with an access point. The Meraki scanning radio captures these probe requests, allowing the cloud controller to triangulate the presence of these devices based on signal strength received by multiple access points in the vicinity. By processing these raw signals, the platform computes metrics such as visitor dwell time, which measures how long a client remains within the coverage area, and repeat visitor patterns, which establish customer loyalty trends. This transformation of raw telemetry into actionable data provides businesses with a visual representation of how visitors navigate physical spaces, effectively turning your network into a high-fidelity occupancy sensor. Achieving high levels of accuracy in these measurements requires careful consideration of your physical infrastructure layout. Because the system relies on signal trilateration, placing access points too far apart or in environments with significant physical obstructions will increase the margin of error in coordinate calculations. You should strive for a dense deployment model where each area of interest is covered by at least 3 access points with clear line of sight to the likely location of mobile devices. Additionally, you must account for the height of the mounting, as signal patterns change significantly between ceiling-mounted units and wall-mounted installations. By optimizing your access point density and ensuring consistent mounting heights throughout the floor plan, you create the necessary environmental cleanliness that lets the location engine identify visitor flow patterns and queue wait times with granular precision. Beyond basic presence tracking, you can leverage Bluetooth low-energy beacons integrated directly into modern Meraki access points to facilitate contextual proximity-based engagement. BLE functions on a different frequency spectrum than Wi-Fi, allowing you to send non-intrusive signals to mobile applications or mobile devices that have authorized interaction protocols. This mechanism is particularly useful for indoor navigation or personalized marketing, as it allows your application to know exactly if a user is standing in front of a specific product display or service kiosk. When combined with the dashboard scanning API, this rich coordinate data can be exported to external analytics platforms or CRM systems for a more holistic view of the customer journey. The API provides a robust stream of JSON-formatted data containing client MACs, signal strengths, and calculated locations, which developers can consume to build custom dashboards or automated operational triggers that respond in near real time. Privacy remains a paramount concern when deploying any system that monitors client presence, and the Meraki architecture includes built-in safeguards to maintain compliance. By default, the system applies MAC address hashing, which replaces the unique hardware address of a device with a randomized identifier before it is stored or processed for analytics. This practice ensures that you can still analyze long-term trends and unique visitor behavior without actually knowing the identity of the specific human behind the device. You must properly configure your dashboard policies to explicitly define how long this data is retained and ensure that your network operations adhere to the regional privacy standards applicable to your physical location. Through smart configuration of these privacy masking tools, you gain the ability to provide deep operational insights while respecting the boundaries and data protection expectations of your visitors. See you in the next lecture. Welcome to the module on switch provisioning, where we will examine how to efficiently deploy and organize Meraki MS switches within scalable campus architectures. Over the forthcoming sessions, you will learn to master dashboard onboarding tools and configuration templates to ensure your network deployments remain both standardized and error-free. When we talk about provisioning Meraki MS switches, the primary objective is to move away from the traditional, manual, per-device configuration model that historically plagued enterprise networking. In a Meraki environment, the concept of zero-touch provisioning is not just a marketing term. It is a fundamental architectural approach that relies on the cloud dashboard as the single source of truth for your device states. Before any physical device is unboxed, you can prepare the network environment by defining organizational settings, firmware baselines, and tagging structures that will automatically apply as soon as the switch gains internet connectivity. This shift requires a change in mindset from local CLI-based management to a declarative state where you describe the desired configuration, and the cloud controller ensures the hardware converges to that state. By utilizing the dashboard's onboarding tools, you reduce the surface area for human error, which is often the silent killer of consistency in large-scale campus rollouts. We will examine how this automation functions during the initial handshake, where the device beacons out to the Meraki cloud and pulls its assigned configuration parameters, effectively eliminating the need for a field technician to interact with a console cable under normal circumstances. Configuration templates represent the most powerful mechanism for enforcing uniformity across a large fleet of switches, particularly when you are managing hundreds of access or distribution layer nodes. Instead of creating redundant configurations for identical roles, you can define a template that encapsulates shared settings such as VLAN definitions, spanning tree parameters, and management interface security requirements. When you bind a switch to a template, the device inherits the global baseline, and you only need to override specific settings on a per-port basis, such as local access VLANs or power over Ethernet configurations. This inheritance model is crucial for maintaining compliance within an enterprise, as it ensures that any security update or policy shift can be cascaded across the entire infrastructure with a single commit command. Furthermore, these templates allow you to manage firmware lifecycles collectively, scheduling updates during predefined maintenance windows to prevent unexpected downtime across critical segments of the network. The efficiency gains are measurable, as the staging process transitions from a repetitive manual task to a streamlined validation workflow, where the technician's primary duty becomes verifying physical connectivity and checking status lights. The mechanics of how these switches initialize are rooted in the device's ability to communicate with the Meraki backend via an encrypted, high-availability control plane. Upon connecting to a network with DHCP and internet access, the switch performs an automatic cloud connectivity checkpoint, where it attempts to reach the dashboard to register itself and retrieve its assigned configuration. During this initial boot process, the device uses the serial number linked to your dashboard organization to identify its deployment slot and apply the appropriate configuration profile. In scenarios where you need to clone switch configurations, the dashboard provides intuitive tools that allow you to take an existing, well-behaved switch configuration and apply its properties to a newly discovered unit. This cloning process is particularly useful for rapid replacement of failed hardware or for duplicating standard port-level security policies across a floor or building. By mastering these cloud-based provisioning tools, You gain the ability to drastically reduce your site deployment timelines while simultaneously adhering to strict enterprise guidelines that define your infrastructure's health and security posture. See you in the next lecture. Welcome back to the course. We are now moving into the configuration of complex, high-availability wired networks by exploring the differences between physical and virtual stacking architectures. When we talk about physical stacking in the context of the Meraki ECMS series, we refer to a design where multiple physical switches are connected via dedicated stacking cables to act as a single logical entity. This architecture allows you to manage a group of switches as one, which significantly reduces the administrative overhead of individual device management. From a data plane perspective, physical stacking provides a massive backplane bandwidth benefit because the switches share a common switching backplane. When electing a stack master, the logic follows a specific priority. The switch with the highest configured priority value wins, followed by other internal criteria, such as the switch model and its current uptime or serial number. In a physical stack, if the master switch fails, a sub-second election process occurs, and a new master takes over without dropping active client traffic, provided the network is correctly configured for high availability. This is critical for deployments where localized hardware bottlenecks must be avoided at all costs. You should always aim to distribute your uplink ports across different physical switches in the stack to ensure that a single switch failure does not isolate your distribution layer from your core infrastructure. Virtual stacking takes a fundamentally different approach, as it does not rely on dedicated physical cabling between units. Instead, it leverages the Meraki Cloud dashboard to synchronize configurations across a large number of switches, regardless of their physical location or model. This is particularly useful in massive enterprise environments where you might have thousands of distributed switch ports across different floors or even different geographic branches. Through the dashboard, you can apply port templates and synchronization settings to ensure that hundreds of switches maintain global consistency in their configuration, such as standardized VLAN assignments or port security settings. While virtual stacking does not provide the unified backplane benefit of a physical stack, it provides a superior operational interface for managing scalability and simplifying the deployment of uniform port policies. It effectively eliminates the need to jump between individual switch pages to make minor adjustments, effectively serving as an abstraction layer for your networking hardware. In many modern designs, you might even see a hybrid approach where physical stacks are connected at the access layer and then managed through virtual stacking constructs at the distribution level for better control. Choosing between these two methodologies forces us to analyze the specific requirements of our layer 2 path redundancy. Physical stacking provides hardware-level redundancy that is immediate and transparent to the devices connected to the access layer, especially when using link aggregation groups that span multiple physical members of the stack. This simplifies spanning tree protocol overhead and usually results in a cleaner, loop-free topology if properly planned. On the other hand, virtual stacking is the backbone of operational efficiency, particularly when you need to maintain a homogeneous environment across heterogeneous hardware. When you design an enterprise distribution layer, your goals are to maximize the bandwidth of your uplinks and ensure that you have clear visibility into port performance regardless of the physical chassis. By contrasting the technical design trade-offs of these frameworks, you ensure that your network remains both resilient against physical hardware faults and easy to maintain throughout the lifecycle of the infrastructure. Carefully consider the physical layout and the availability of high-speed stacking ports before deciding if a physical stack is necessary or if a virtual management strategy provides a more scalable path for your long-term bandwidth requirements. See you in the next lecture. Welcome back. Let us discuss how to implement scalable segmentation and dynamic inter-VLAN routing directly on your Meraki ECMS switches. When we transition routing workloads from the edge firewall down to the L3 capable switches, we fundamentally change the traffic flow within our campus network. In smaller environments, the firewall often acts as the default gateway for every VLAN, which can quickly saturate the uplink ports and tax the firewall CPU during heavy inter-VLAN traffic. By configuring switched virtual interfaces on the Meraki ECMS series, we anchor the Layer 3 gateway closer to the end devices. This approach keeps local subnet traffic off the firewall, allowing the switch fabric to perform the routing at line rate using hardware-based ASICs. Configuring an SVI requires a VLAN to be defined globally on the switch, followed by assigning an IP address to that specific interface within the switch's Layer 3 settings. This mechanism ensures that as long as the switch knows how to reach the destination subnet, it handles the inter-VLAN routing internally without traversing the core link. Static routes remain a foundational tool for directing traffic toward networks that aren't directly attached to our switch, such as remote branches or a centralized data center. While static routes are simple to configure via the dashboard, they don't respond to topology changes, so we must be precise when defining the next hop IP addresses. In a multi-subnet environment, clients often require assistance to obtain IP information when they span multiple broadcast domains. Here, the DHCP relay agent functionality becomes critical, as it captures the broadcast DHCP discovery packets and tunnels them to a centralized server. You must configure the helper address on the SVI that serves as the gateway for your clients, ensuring the switch knows exactly where to forward those requests across the routed path. This eliminates the need for maintaining individual DHCP pools on every switch and keeps address management centralized at the core of your infrastructure. For environments requiring more resilience and automated path discovery, dynamic routing via the Open Shortest Path First protocol is the preferred choice over static entries. OSPF operates by exchanging link state advertisements between neighboring routers, allowing the switch to maintain an accurate map of the network topology. When you enable OSPF on a Meraki switch, you must define the area ID and identify which interfaces participate in the routing process. The switch then automatically calculates the shortest path to every known destination based on the reference bandwidth, which is a significant improvement over manual configuration. If a link fails or a cost changes, the OSPF process updates the routing table in real time without administrative intervention. However, keep in mind that mixing OSPF and static routing requires a solid understanding of administrative distances to ensure the preferred route is always the one installed in the routing information base here. Understanding how a switch handles packet delivery involves more than just enabling protocols. It requires analyzing how the routing table selects the best path through your switch architecture. Routers always prefer the most specific prefix length, meaning A24 route will always override A/16 route for the same traffic. We often use link aggregation groups to bundle multiple physical trunk links into a single logical high bandwidth channel between core and distribution layers. When configuring these bundles, you ensure that inter-VLAN traffic experiences minimal latency because the switch can distribute the frames across all physical fibers simultaneously. When traffic enters a switch, the ASIC performs a lookup against the forwarding information base, which holds the current routing decisions ready for immediate use. Consequently, the switch hardware processes frames at wire speed, ensuring that high-bandwidth internal data transfers do not impact the performance of external internet connectivity handled at the firewall. Effective design requires us to balance the containment of broadcast domains with the need for high-speed inter-subnet communication. By placing the SVI at the distribution layer, you effectively shrink the broadcast domain, which minimizes the overhead of ARP requests and unnecessary traffic noise across the access layer links. A well-designed campus core acts as the backbone for this traffic, utilizing high-bandwidth trunks to interconnect the L3 switches. You must routinely monitor the transit flows to confirm that traffic is traversing the intended path through your virtual interfaces. If you notice unexpected latency during internal transfers, checking the hardware load and verifying the path cost for your OSPF neighbors is usually the first objective step in troubleshooting. Keeping the routing logic as close to the source as possible is the hallmark of a resilient and performant network infrastructure. See you in the next section. Welcome to our deep dive into the spanning tree implementation within Meraki environments. In this chapter, we will master the logic of loop prevention and deterministic path selection. Spanning tree protocol remains a fundamental mechanism for ensuring that Ethernet networks remain loop-free while providing redundancy. In a Meraki switching environment, understanding how to influence the topology is crucial because broadcast storms can bring an entire production network to a halt in seconds. While Meraki switches strive to automate much of this through rapid spanning tree protocol, there are scenarios where the default behavior is insufficient for your specific requirements. You need to be able to explicitly define which switch acts as the root bridge to ensure consistent traffic flows across your wired architecture. By manually tuning bridge priorities, you prevent the selection process from falling to an underpowered or improperly positioned edge switch, which could lead to suboptimal traffic, hairpinning, or latency spikes. I often compare this to traffic engineering in a metropolitan area, where you want to ensure the main arteries are always utilized by the primary throughput, not random side roads. Relying on default configurations is a recipe for unpredictability when hardware undergoes unexpected power cycles or fiber links fail. The primary tool at your disposal for controlling this process is the bridge priority setting, which ranges from 0 to 61,440 in increments of 4,096. A lower priority value makes a switch more desirable to become the root bridge, meaning the switch with the lowest priority wins the election process. When you design your topology, you should identify your core or distribution switches and assign them the lowest priority values, perhaps 0 for the primary route and 4096 for the secondary candidate. This stability is essential because whenever there is a root bridge change, the entire network undergoes a reconvergence event that can cause momentary packet loss. You want this convergence to be as rare as possible in a stable environment. In the Meraki dashboard, this is configured per switch, where you define the priority to force the network to converge exactly how you have modeled it in your head. Setting these values manually moves you from a passive observer of network behavior to an active architect of traffic flows. Beyond route placement, we must discuss the specialized guard features that Cisco Meraki provides to protect the integrity of the spanning tree state. BPDU Guard is one of the most critical security features to enable on any port configured as an access port for end devices. When BPDU Guard is enabled, the port will immediately disable itself if it receives a bridge protocol data unit, which is a clear indicator that a switch has been plugged into a port where only a client device should exist. Similarly, Root Guard behaves differently by preventing a port from ever becoming a root port, regardless of the BPDUs received on that interface. This is vital when you connect to a third-party managed environment or a different administrative domain where you want to ensure their switches cannot ever become the root bridge of your network. LoopGuard provides an extra layer of safety by transitioning a port into a loop inconsistent state if BPDUs are stopped unexpectedly on a redundant link, effectively preventing a loop from forming due to unidirectional link failures. Monitoring and diagnostic capabilities in the cloud are what transform Spanning Tree from a black box into a manageable component of your infrastructure. When you encounter connectivity issues, the first step is often to review the event logs within the Meraki dashboard for any TCN or topology change notifications. These logs inform you exactly when and where a spanning tree state transition occurred, allowing you to trace the event back to a specific interface or a flapping physical link. If you see frequent TCN logs, it is a definitive sign that a device is oscillating or a cable is faulty, leading to the continuous recalculation of the network topology. Using cloud-based diagnostic tools, you can examine the path cost on specific interfaces to determine if the path being chosen by the protocol is indeed the most efficient one for your throughput needs. If you detect that traffic is being routed through an unintended link, you can quickly adjust your priority values or port costs without having to physically visit the site or log into a command line interface. This level of granular visibility ensures that even complex wired topologies remain predictable and reliable over the long term. See you in the next lecture. Welcome to the chapter on quality of service, where we will focus on designing and executing strategies to protect your critical real-time communication streams. We will master the classification and prioritization techniques necessary to ensure jitter-free, high-quality voice and video performance across your Meraki switching infrastructure. In the context of modern enterprise networking, quality of service is the deliberate intervention required to ensure that time-sensitive traffic receives preferential treatment over best effort data. When we operate in a shared medium, congestion is an inevitable reality during periods of high utilization. Without a clear strategy, your voice over IP and video conferencing packets compete equally with background file transfers or general web traffic. This contention results in delayed delivery, jitter, and dropped frames, ultimately degrading the user experience. By implementing robust classification at the edge, you effectively label traffic based on its importance to the business. We utilize class of service markings at layer 2 and differentiated services code point values at layer 3 to ensure that switches understand exactly how to handle every frame that traverses the network. Classifying traffic effectively means identifying the nature of the data before it even enters the switching fabric. When a packet arrives at an access port, we inspect it and map its existing markings or apply new ones based on the traffic source or protocol signature. This mapping process is critical because it dictates how the hardware places the packet into specific egress queues. Meraki switches typically support multiple hardware queues, ranging from low priority for background bulk data to strict priority queues for latency-sensitive traffic. By configuring strict priority queuing profiles, you force the hardware to process high-priority packets before clearing any other buffers. This ensures that a voice packet is never stalled behind a large data transfer, which is the most common cause of audio degradation in voice networks. Bandwidth management often involves more than just prioritization. It requires proactive rate limiting and traffic shaping controls. On a per-port basis, you can restrict the amount of bandwidth available to specific devices or applications to prevent a single user from overwhelming an uplink. While shaping involves buffering traffic to smooth out bursts, policing or rate limiting often involves dropping traffic that exceeds a defined threshold to enforce policy compliance. In congested environments, such as a busy uplink connected to a core switch or firewall, shaping is essential to handle bursts without discarding high-priority frames. We must carefully balance these settings to provide enough buffer depth for bursty video traffic while maintaining the tight latency constraints required for real-time applications. Observing the impact of your changes through the dashboard's flow statistics will lead you to an optimized bandwidth allocation that effectively eliminates bottlenecks. Optimizing the configuration requires an understanding of the relationship between your marking strategy and the switch's internal queuing architecture. When you apply a policy, the switch analyzes the packet's DSCP or CoS field and assigns it to a hardware queue based on the predefined mapping. If your infrastructure is misconfigured, even the highest priority markings might be ignored if the switch defaults to a first-in, first-out delivery model. Consistently applying these markings throughout the network path ensures that the logic you implement at the access layer is respected by the distribution and core layers as well. Verification is straightforward through the use of performance metrics and traffic analysis, which reveal whether your critical streams are hitting the intended queues. By mastering these foundational mechanisms, you move beyond basic connectivity and provide a reliable, predictable environment for the most sensitive communication tools in your organization. I look forward to our next session together. Welcome back to our exploration of Meraki switching infrastructure. In this section, we move our focus to the edge, specifically addressing how we secure the physical points of entry into your wired network. Securing the physical switch port is often the most overlooked aspect of enterprise networking, yet it remains the primary vector for unauthorized access. When we talk about port policies on an MS switch, we are effectively defining the boundary between trusted and untrusted hardware. By moving security enforcement to the port interface level, we stop threats before they propagate into the core of the network. This approach to zero-trust architecture requires a deliberate configuration of authentication protocols and hardened settings. We will examine how these policies interact with both the Meraki cloud and the local switching silicon to identify and contain potential risks. Mastering these configurations allows you to enforce strict standards for every device connecting to your physical infrastructure, regardless of where that device originates. The cornerstone of modern port security is 802.0x authentication, which requires a radius server to validate identity before granting network access. When you enable this on a port, the switch acts as an authenticator, blocking all traffic except APOL frames until the client provides valid credentials. For legacy devices or simple IoT endpoints that do not support 802.x supplicants, we utilize MAC Authentication Bypass, or MAB. While MAB is inherently less secure because it relies on the spoofable MAC address as an identity, it serves as a necessary fallback for heterogeneous environments. You must decide whether to use single auth mode, which pins the port to the first authenticated device, or multi-auth mode, which allows multiple independently authenticated devices behind a single physical drop. Careful consideration of these host modes prevents unauthorized hardware from daisy-chaining off a single secure port. Beyond identity, we must secure the communication streams themselves using DHCP snooping and dynamic ARP inspection. DHCP snooping builds a trusted binding database that correlates specific MAC addresses with allocated IP addresses on legitimate ports. When you explicitly define trusted uplinks and untrusted access ports, the switch begins to drop illegitimate DHCP replies from rogue servers that might attempt to perform man-in-the-middle attacks. Dynamic ARP inspection takes this a step further by intercepting ARP packets and cross-referencing them against the DHCP snooping database. If a device attempts to broadcast an ARP reply with a spoofed IP to MAC mapping, the switch discards the frame immediately. These features transform a simple L2 port from a passive conduit into an active security enforcement point that continuously validates the integrity of every frame. To further minimize your attack surface, we should discuss administrative hardening through sticky MAC limits and port scheduling. Sticky MAC limits allow you to enforce a maximum number of unique hardware addresses permitted on a specific port, effectively preventing MAC flooding or unauthorized device expansion. By setting this limit to 1, you ensure that only the primary intended device is ever permitted to communicate, causing the port to shut down if a secondary device is introduced. Simultaneously, port scheduling provides a mechanism to reduce the exposure of physical ports during times when they are not in use, such as after business hours. By automatically disabling ports, you remove the physical reachability of the network, which is a surprisingly effective way to limit site-wide lateral movement. These policies are not just about compliance, they're about maintaining a predictable network state that leaves no room for ambiguous hardware behavior. When we integrate these policies into the Meraki dashboard, we gain a unified view that simplifies the management of what would otherwise be a complex set of CLI commands. The ability to deploy these configurations across an entire organization with a single click is what makes the Meraki solution uniquely scalable in modern deployments. You must balance the strictness of your security posture with the operational requirements of your users to avoid unnecessary help desk overhead. If you implement too strict a policy without proper radius testing, you risk isolating legitimate endpoints and causing service interruptions. I recommend starting with monitor mode to observe existing traffic patterns before transitioning ports to fully enforced security profiles. This methodical approach ensures that your hardening efforts reinforce the network rather than disrupting its core availability. See you in the next lecture. Welcome to this exploration of appliance deployment, where we will master the configuration of Meraki MX security gateways for enterprise edge environments. You will learn how to design resilient routing topologies and implement specialized deployment modes that ensure your network remains robust against failures. Deploying Meraki MX appliances involves more than just plugging in cables and claiming devices in the dashboard. You must first consider the topological requirements of your edge perimeter, specifically regarding how the MX behaves in relation to your existing WAN architecture. In a standard routed mode, the appliance acts as the primary gateway, handling NAT, security services, and site-to-site VPN termination. However, enterprise environments often require a one-armed VPN concentrator mode, where the MX sits away from the main traffic path to handle VPN traffic exclusively. In this setup, you must ensure that static routes are correctly configured so that return traffic from the internal network reaches the VPN concentrator, or you risk asymmetric routing issues. Understanding the traffic flow is non-negotiable because the Meraki cloud relies on predictable pathing to maintain overlay tunnels. By isolating the VPN function, you gain the ability to scale security processing independently from your core switching assets. Resiliency at the edge is primarily achieved through the implementation of dual uplink WAN parameters and high-availability warm spare topologies. When configuring multiple uplinks, the MX evaluates upstream connectivity using ICMP probes or DNS lookups against reliable endpoints to determine link health. You can designate primary and secondary uplinks to steer critical traffic, effectively creating a fallback mechanism that triggers when throughput thresholds or latency triggers are violated. To prevent a single appliance failure from disrupting the entire site, you should implement a warm spare pair using the virtual router redundancy protocol. In this configuration, one appliance is designated as the primary and the other as the spare, sharing a virtual IP address that serves as the default gateway for local clients. Should the primary device stop responding to keep alive heartbeats sent by its peer, the secondary appliance promotes itself to active status. This failover process is transparent to end devices, although short-lived TCP sessions may reset during the transition state as the MAC address propagates through the local forwarding table. Beyond physical hardware, modern enterprise strategies often require virtual MX deployments within public cloud environments like AWS or Azure. A virtual MX provides the same auto VPN and security capabilities as its physical counterpart, allowing you to extend your SD-WAN fabric directly into your cloud VPC or VNet. When deploying in the cloud, you are essentially creating a virtual security perimeter that acts as a gateway for your public cloud workloads. You must pay close attention to cloud-specific routing constructs, such as route tables and subnet associations, to ensure that traffic is directed through the virtual appliance as intended. These virtual instances support the same high availability scenarios as physical devices, often utilizing cloud-native load balancing or service chaining to ensure traffic continuity. Mastering this transition from physical to virtual appliances allows for a consistent security posture across your entire hybrid infrastructure, regardless of where the data resides. See you in the next session. Welcome back. In this chapter, we will explore the capabilities of Meraki Auto VPN, focusing on how cloud orchestration simplifies complex site-to-site connectivity. Meraki Auto VPN represents a fundamental departure from traditional manual IPsec implementations that require individual configuration of crypto maps, IKey parameters, and transform sets on every peer. Instead, the Meraki Cloud Controller acts as a central orchestrator that abstracts these low-level security association tasks into a simplified administrative interface. When you enable the Auto VPN service, the local MX appliances securely authenticate with the Meraki Cloud backend using TLS and provide their current public IP addresses and local subnet information. The controller then intelligently builds a dynamic map of your entire network topology, distributing the necessary peer lists and shared keys to each participating site automatically. This means that if a remote spoke appliance changes its WAN IP due to a DHCP refresh, the cloud orchestrator immediately propagates this change to the hubs and other spokes. The complexity of dynamic NAT traversal, which often breaks standard IPsec VPNs, is handled transparently by the cloud-mediated connectivity, allowing for robust communication even when appliances reside behind restrictive NAT devices or asymmetric internet connections. You no longer need to worry about manually synchronizing PSKs across a dozen sites, as the system provides an automated and secure key management lifecycle that scales as your branch network grows. When architecting these wide area topologies, you have the flexibility to define specific roles for your Meraki appliances, categorizing them as either hubs or spokes based on the needs of your organization. In a hub and spoke model, the hub appliances typically reside in data centers or regional offices and are responsible for advertising their local subnets to all spokes, effectively providing a transit point for reachability. By configuring redundant data center hubs, you introduce high availability, as the spoke appliances can be configured to prefer one hub over another, or load balance traffic between primary and secondary hubs if both are available. For scenarios that demand more direct communication, such as distributed database synchronization or peer-to-peer VoIP IP, you can opt for a full mesh topology where every site establishes a direct encrypted tunnel to every other site in the network. If a full mesh design introduces too much overhead, a partial mesh configuration allows you to define specific hub-to-spoke relationships while maintaining direct tunnels only where performance requirements strictly mandate them. The ability to manipulate the routing information exchanged across these tunnels is further enhanced by VPN exclusion lists. These lists provide a surgical method for preventing specific subnets from being advertised over the VPN, which is particularly useful when you need to prevent routing loops or ensure that certain local traffic stays entirely within a physical branch rather than being backhauled through a central VPN site. Mastering these automated orchestration mechanics provides a significant operational advantage, as it removes the human element from the crypto configuration layer, where most site-to-site failures originate. Because the system continuously monitors the health of the tunnels, it can perform active health checks to ensure that a tunnel is not just logically up, but actually passing traffic before routing decisions are made. This visibility is coupled with the ability to define traffic-specific rules that determine whether traffic should traverse the VPN or go out through a local breakout, a topic we will build upon as we discuss SD-WAN steering policies. By abstracting the IPsec lifecycle, you gain the agility to provision a new branch in minutes rather than hours, maintaining a consistent security posture across the entire organization without the need for specialized manual intervention at the edge. The cloud management plane ensures that even in massive deployments with thousands of branches, your security parameters remain synchronized and your reachability information remains accurate. Relying on this automated backbone allows your infrastructure to adapt to changing network conditions, such as WAN, ISP failures, or link degradation, without requiring you to manually re-engineer the underlying VPN architecture. As these encrypted backbones are built over any common internet connection, from standard broadband to dedicated fiber, you can standardize your design regardless of the underlying hardware or ISP provider at each specific location. See you in the next lecture. Welcome back to our discussion on Meraki SD-WAN capabilities. In this session, we will explore the mechanisms behind intelligent traffic steering and how to ensure your wide area network remains resilient and performant. Traffic steering within the Meraki SD-WAN framework is not merely about choosing a path of least resistance, but rather about programmatic intent applied to network flows. When we discuss dynamic path selection, we are essentially talking about the continuous evaluation of performance metrics across multiple uplinks, including MPLS, broadband, and cellular connections. The dashboard allows us to define specific performance thresholds expressed in terms of latency, packet loss, and jitter. When a particular application, such as a voice-over IP service or a mission-critical cloud platform, exceeds these predefined thresholds on the primary path, the appliance automatically redirects that traffic stream. This decision-making process happens in real time, relying on the stateful tracking of connection quality rather than static routing metrics like cost or hop count. By establishing these granular policies, we shift the burden of manual failover away from administrators and into the intelligent fabric of the network itself. To implement an effective steering strategy, we must first categorize traffic based on its performance sensitivity. A voice session is notoriously intolerant of jitter, whereas a background data backup is relatively indifferent to minor latency spikes. We configure these requirements within the SD-WAN policies, where we can define what constitutes a performance violation for specific traffic classes. Once the criteria are set, the appliance actively probes the health of every available uplink, measuring round-trip time and packet loss consistently. This active monitoring is critical because it reveals the true state of the middle mile and the ISP transit paths, which are often beyond our direct control. When a threshold is violated, the transition to an alternate link is seamless, provided that the secondary path actually meets the performance requirements we have established. Using active load balancing ensures that we are not letting expensive bandwidth sit idle, while simultaneously protecting our most vital traffic from common internet instability. Managing cellular failover adds another layer of complexity to our traffic distribution logic. We often treat LTE or 5G connections as a secondary resource due to data caps or variable performance profiles. Within the dashboard, we can set specific policies that dictate when the appliance should bring a cellular link online and, just as importantly, when it should be relegated back to standby mode. We might allow high-priority traffic to fail over to cellular while actively blocking lower-priority services from consuming cellular airtime during an outage. This is achieved through policy-based routing exceptions that provide the necessary granularity to influence the path selection algorithm beyond the bulk traffic preferences. We are essentially building a declarative model where the network behaves according to business rules rather than reactive manual intervention. This level of precise control is what allows us to maintain the integrity of our cloud-based platforms even when the underlying connectivity experiences turbulence. See you in the next lecture. Welcome back. Today we are going to dive into the core mechanics of the Meraki MX firewall engine to secure your network perimeter. We will explore how to construct granular security policies that protect your infrastructure from both inbound and outbound threats. The foundation of the MX firewall architecture relies on an explicit processing order that every administrator must understand to avoid unexpected traffic drops. When you configure rules in the dashboard, the appliance evaluates them from the top of the list downward, meaning the first matching rule dictates the action taken for a given packet. This top-down hierarchy is non-negotiable. Once a match is found, the appliance executes the allow or deny action and stops further evaluation. Consequently, you must place your most specific rules at the top, such as those addressing critical internal servers or specific departmental subnets. Catch-all rules, which are typically designed to deny all remaining traffic, should always reside at the very bottom of your policy list to ensure that only authorized traffic persists through the perimeter. Misconfiguring this order is the most common cause of connectivity issues in complex environments, so always verify your logic during the deployment phase. Beyond simple port-based filtering, the MX engine allows for sophisticated Layer 7 application control, which inspects traffic based on signatures rather than just IP addresses or TCP ports. By leveraging the deep packet inspection capabilities of the Meraki cloud, you can write rules that permit or block specific applications like BitTorrent, Facebook, or unauthorized cloud storage services regardless of the ports they attempt to use. This capability is instrumental in preventing data exfiltration and maintaining compliance within regulatory environments where external access must be strictly defined. You can also implement geo-IP blocking to drop traffic originating from specific countries that do not align with your business operations. This adds a critical layer of defense as it proactively eliminates the attack surface by refusing communication attempts from regions where you have no legitimate users or clients. When managing environments with cellular failover or dedicated LTE uplinks, controlling data consumption is a vital aspect of operational cost management. You can configure cellular-specific constraint rules that restrict bandwidth-heavy applications from utilizing the cellular interface, thereby preserving expensive data plans for mission-critical traffic. By building explicit cellular path rules, you define exactly which types of traffic are permitted to transit over the wireless link, effectively isolating high-volume traffic to your primary broadband connections. This requires a clear understanding of your traffic patterns, as an incorrectly configured cellular rule could inadvertently throttle essential business processes during a primary site failure. Always monitor your cellular usage via the dashboard when these constraints are active to ensure that your business continuity goals remain aligned with your hardware configuration. Managing inbound traffic requires a robust implementation of NAT mappings, including both one-to-one, many configurations to expose internal resources to the public internet securely. 1. One NAT is typically reserved for scenarios where a single internal device, such as a web server, must be reachable via a specific public IP address without port translation complications. In contrast, 1. Mini-NAT allows you to map a single public IP to multiple internal devices by utilizing distinct port forwarding rules, which conserves your public IP address space. These inbound forward rules must be coupled with strict logging policies to ensure that every blocked connection attempt is recorded for audit and compliance purposes. By enabling logging on your perimeter rules, you gain the visibility required to identify reconnaissance activity or brute force attacks against your exposed services, which is essential for maintaining a mature security posture. I will see you in the next lecture. Welcome to the module on content filtering, where we will examine how to enforce web policies and mitigate threats directly at the network edge. Mastering these configurations is essential for any engineer tasked with securing modern distributed network environments. In this chapter, we focus on the mechanics of URL content filtering and Cisco umbrella integration within the Meraki platform. We will move beyond simple block lists to consider how category-based filtering, safe search enforcement, and deep packet inspection of HTTPS traffic contribute to a robust security posture. By the end of these lessons, you will understand how to leverage group-based policies to balance end-user productivity with the strict compliance requirements of your organization. We will look at the implementation of whitelists for exceptional traffic patterns and the nuances of handling user-specific overrides. You will gain the expertise required to reduce your organization's exposure to web-borne malware and unauthorized content, ensuring that your network perimeter remains resilient against evolving digital threats. When we approach content filtering in a Meraki environment, the primary objective is to move the enforcement point as close to the user as possible, typically at the security appliance. URL filtering starts with the category-based engine, which allows administrators to categorize millions of websites and apply block or allow actions based on those classifications. This is a powerful tool because it relieves the administrator of the burden of maintaining individual blacklists, which is a futile task in a world where new malicious domains appear every second. When you enable these categories, the Meraki appliance effectively consults its local database or the cloud-based reputation service to decide whether to permit the flow. It is important to remember that these settings are typically applied to specific group policies or the default network-wide policy, allowing for granular control that scales across large, multi-site deployments. Enforcing safe search is a straightforward but often overlooked component of productivity management and compliance. By enabling safe search, the Meraki MX forces the inclusion of specific parameters in search engine requests, essentially ensuring that the search providers filter adult content from their result sets before they ever reach the user's browser. Beyond general category and safe search blocks, you may encounter scenarios where business requirements necessitate the access of specific domains that would otherwise fall into a blocked category. This is where explicit URL whitelists become vital, as they provide an override mechanism that keeps your security policy intact while supporting essential business operations. Managing these lists requires a disciplined approach to ensure that you are not inadvertently opening back doors into your network for malicious actors. So always restrict whitelist entries to the most specific patterns possible. Modern web traffic is predominantly encrypted, which creates a significant challenge for traditional URL filtering mechanisms that rely on packet headers. To inspect the traffic within these encrypted flows, you must configure HTTPS decryption, which involves the Meraki appliance acting as an intermediary to terminate the SSL-TLS connection. While this enables the inspection of URL patterns and payload content, it introduces complex requirements regarding certificate management, as client devices must trust the certificate issued by the appliance to avoid warnings. Once the inspection is active, the engine can distinguish between different paths on the same host, which is a crucial capability for modern web application security. Properly planning this deployment involves balancing the necessity for visibility against privacy constraints and the processing overhead of the security appliance. Flexibility of the Meraki architecture shines when we integrate user identity into the filtering workflow. By utilizing Active Directory or Systems Manager group tags, you can tailor content filtering schedules and policies to different segments of your workforce. For example, your marketing department might require access to social media tools that are restricted for other users, and these policies can be synchronized seamlessly with existing user profiles. This group-based approach also simplifies the management of user override requests, as you can grant temporary exceptions for specific identities rather than modifying global network settings. Effectively managing these profiles reduces the support load on your IT team and keeps the security policy aligned with the evolving needs of the different departments within your organization. See you in the next lesson. Welcome back. Today we are diving into threat protection to secure the network edge using advanced Meraki MX security features. Securing the modern perimeter is no longer a matter of simple stateful packet inspection, as adversaries evolve their methods to bypass traditional firewalls. On the Meraki MX platform, we implement a multi-layered defense strategy centered on Snort, which serves as the engine for both intrusion detection and intrusion prevention systems. When we enable these features, we are essentially deploying a signature-based detection mechanism that continuously monitors incoming traffic against a vast, cloud-updated database of known malicious patterns. You have two primary modes of operation available when configuring these security profiles: detection and prevention. In detection mode, the system acts as an IDS, logging the event for administrative review without blocking the flow, while prevention mode enables the IPS to actively drop packets that trigger a signature match. Choosing the right profile is critical, as it requires balancing the sensitivity of detection against the necessary throughput for your specific network environment. Beyond signature-based detection, the MX platform leverages Cisco Advanced Malware Protection, which provides a gateway-level safeguard against sophisticated threats. When a file transit occurs across the gateway, the MX calculates a file hash and queries the Cisco Global Threat Intelligence database to determine if the object is known to be malicious. Many might assume this process blocks everything instantly, but the true power of this system lies in its ability to perform cloud sandboxing for unknown files. If a file does not have a clear reputation, it can be sent to the sandbox for dynamic analysis, where the system executes the file in a secure, isolated environment to observe its behavioral characteristics. This adds a critical layer of latency-aware security, ensuring that you are not simply relying on historical signatures, but on real-time execution telemetry. This capability is instrumental in stopping zero-day attacks that have not yet been categorized by traditional vendors. A significant challenge in enterprise environments is the problem of previously cleared content that is later identified as malicious by updated intelligence. Cisco AMP solves this through the mechanism of retrospective malware notifications, which provide administrators with visibility into the long-term impact of file transfers. If a file was allowed through the gateway at a time when its hash was not yet marked malicious, the system can retroactively flag that event if the intelligence database receives an update. This gives us the ability to isolate infected internal systems quickly, as we are notified exactly which client machines interacted with the now compromised file. Managing these threats effectively requires us to use the Security Center dashboard, where we can analyze security threats in aggregate and drill down into specific incident timelines. This analytical visibility is mandatory for anyone looking to pass the Solution Specialist exam, as it demonstrates a complete mastery of the threat lifecycle. When you encounter a legitimate business application being incorrectly flagged by the IPS, you must understand how to manage signature exception lists. These lists allow you to whitelist specific signatures that interfere with operational traffic without globally disabling the entire security profile for your network. It is important to remember that every exception you create inherently weakens your security posture, which is why we must always document the reasoning behind each whitelist entry. Furthermore, while the Security Center provides excellent built-in analytics, you should consider how the information gathered here influences your broader security policy, such as adjusting traffic shaping or firewall rules. Effectively neutralizing advanced persistent threats is a continuous process of tuning these defense engines to be as automated as possible. By integrating Snort and AMP, you create a robust perimeter that is capable of evolving alongside the threat landscape. I look forward to discussing how these security configurations integrate with our wider management workflows in our next session. Welcome back. In this session, we will examine the mechanisms required to establish automated enrollment pipelines for mobile device management within the Meraki Systems Manager ecosystem. Effective endpoint management begins with a robust enrollment strategy that minimizes manual intervention while ensuring consistent security posture across diverse hardware platforms. When we discuss Apple Automated Device Enrollment, we are essentially leveraging the synchronization between the Apple Business Manager portal and the Meraki dashboard, which allows devices to be managed at the hardware level from the moment they are unpacked. This integration ensures that the device is supervised, preventing users from removing the management profile or bypassing corporate restrictions. Conversely, for Android environments, we utilize Android Enterprise Deployment Paths, specifically focusing on the device owner mode for corporate hardware. This process involves establishing a managed Google Play account profile, which grants the dashboard granular control over applications and system configurations without requiring the user to navigate complex local settings manually. When we cannot rely on zero-touch provisioning due to legacy hardware or procurement channels, we must fall back on manual enrollment methodologies, such as the use of enrollment web links or standardized QR codes. These methods are particularly relevant for user-owned hardware, often categorized under Bring Your Own Device initiatives, where privacy and separation of personal and corporate data are primary concerns. When a user scans a QR code or visits an enrollment link, they effectively initiate a handshake that delivers the necessary root certificates and management profiles to their local trust store. It is important to remember that these enrollment profiles must be cryptographically signed, as the integrity of the initial trust relationship determines the efficacy of subsequent security policies. By standardizing these pipelines, we create a predictable environment where each device is identified, categorized, and assigned the correct configuration profile before it ever attempts to access internal resources. A critical component of this process is the configuration of enterprise device owner profiles, which dictate the extent of our administrative visibility and control over the endpoint. In supervised operation modes, specifically on iOS, we can enforce mandatory profiles that control everything from Wi-Fi connectivity to the ability to install unauthorized applications. Managing ownership certificates is equally important, as these are the mathematical proofs that certify the device belongs to the organization and is authorized to receive sensitive configurations. We should treat these certificates as first-class citizens in our security architecture, ensuring they are automatically renewed and revoked as devices enter or leave the management scope. Furthermore, optimizing authentication integrations allows us to tie the enrollment process directly to our existing identity providers, ensuring that only users with valid corporate credentials can successfully register their devices. By architecting these automated flows, we transform the chaotic prospect of onboarding hundreds of heterogeneous devices into a replicable, systematic operation. This ensures that every entry point into our network is accounted for and that security policies are applied at the earliest possible stage in the device lifecycle. When we automate this, we are essentially building a gatekeeper that verifies the device's legitimacy before any data exchange occurs, thereby reducing the burden on IT support teams who would otherwise handle these tasks manually. We must always strive to remove the human error factor from the onboarding process because the security of our entire infrastructure is only as strong as its weakest endpoint. Once these pipelines are established, the dashboard becomes the single source of truth for our entire fleet, providing the visibility needed to maintain compliance over the long term. Until then. Hello. In this chapter, we will explore the mechanisms behind profile configuration to automate endpoint management within the Meraki environment. If you are looking to scale your infrastructure management without a linear increase in IT headcount, mastering profile configuration is essential. This chapter provides the technical foundation for enforcing operational standards and security settings across diverse mobile and desktop endpoints. You will learn how to transition from individual device handling to systemic automation, ensuring your fleet remains compliant and configured correctly at all times. Configuration profiles in Systems Manager function as digital blueprints that define how an enrolled device communicates and behaves within your environment. When we talk about granular enforcement, we are essentially talking about the ability to push specific payloads, such as Wi-Fi credentials, email exchange settings, or VPN parameters, to targeted devices without creating overhead for the end user. Consider a scenario where you have 100 remote employees needing access to the corporate intranet via a secure VPN tunnel. Instead of manual setup, you define a payload that includes the VPN server address, the authentication protocol, and the pre-shared key or certificate. Since the Meraki Cloud Platform manages this distribution, the profile is pushed once the device checks in, effectively setting up the connection parameters during the next enrollment phase or configuration sync. Managing these distributions effectively requires a deep understanding of scoped application, which is where dynamic tags play a primary role. Rather than assigning configurations to a single static device, you assign them to a tag, such as sales team or finance department. When a new device is enrolled and assigned that specific tag, the configuration profile automatically flows down to it without any manual input from the administrator. This is crucial for maintaining security consistency, as it ensures that sensitive data, like root certificates required for internal portal authentication, is never missing from a newly deployed machine. Furthermore, you can apply these settings based on location-aware policies. If a device detects it is geofenced outside of a specific office region, you can enforce stricter firewall rules or restrict access to certain enterprise apps as part of the profile orchestration. Operational consistency also depends on how you manage the lifecycle of your settings, particularly through versioning and iterative updates. Environments change, and passwords expire, or VPN concentrators get redeployed to new hardware, requiring a seamless way to push updates to existing configurations. Meraki profiles allow you to iterate on these payloads and update entire groups of devices simultaneously. You might start with a baseline configuration for general corporate users and add specific email exchange profiles only to devices tagged with management status. Because these changes happen in the background through the cloud-managed agent, the end user rarely notices the shift in their security posture, which prevents the inevitable support tickets that come with manual reconfigurations. When architecting these profiles, it is important to think about the order of operations and the precedence of your policies to avoid configuration conflicts. Profiles are applied in a tiered structure where global standards can exist alongside role-specific granular requirements. If we define a broad policy for password length at the organization level, We can layer additional security restrictions on top of that for the HR department specifically. By organizing your profiles into logical buckets, you reduce the complexity of troubleshooting errors when a device fails to pull a setting correctly. Keep in mind that a configuration is only as effective as the enrollment state of the device. So ensure that the communication path between the Meraki cloud and the systems manager agent is robust and verified before pushing critical network changes. See you in the next part. Welcome back. This chapter focuses on mastering application lifecycle management through the Meraki Systems Manager platform to ensure your managed endpoints remain compliant and productive. Building a robust application deployment strategy requires moving beyond manual installation toward a fully automated lifecycle approach within the Meraki dashboard. By leveraging Systems Manager, administrators can define specific software sets for various device groups, ensuring that the right tools are available to the right users automatically. This process begins with integrating external ecosystems, such as the Apple Volume Purchase Program and Google Play for Work, which serve as the foundation for modern enterprise software distribution. Once these services are linked, you gain the ability to push licenses and applications directly to managed devices without requiring individual user intervention. Managing these assets centrally reduces the administrative burden significantly, while providing a clear audit trail of software distribution across the corporate environment. Efficient deployment is not merely about pushing files. It is about establishing a controlled state where you can verify that every device adheres to the organization's software policies. To initiate these workflows, you must first connect your Apple VPP and Google Play tokens within the Systems Manager settings in the dashboard. This integration acts as a synchronization bridge, allowing the Meraki cloud to communicate directly with storefront services to fetch metadata and license information for your elected applications. When you add a new application to your deployment list, you assign it to specific tags or device groups, which triggers the installation sequence on target hardware. For Apple devices, especially those that are supervised, this process is seamless, as the management profile can trigger silent installations that do not require any confirmation from the user. This capability is critical for maintaining consistency in software versions, as it prevents users from running outdated or unsupported applications that might introduce security risks to the network. You should prioritize the use of managed installation accounts to handle the lifecycle of these applications, from initial deployment through the inevitable requirement for updates or eventual removal. Application distribution is often complex when dealing with localized scheduling and varying hardware requirements across an enterprise. You can configure installation behaviors by specifying whether an application should install automatically upon enrollment or during specific time windows designated by your maintenance policies. This is particularly useful when deploying larger software packages that might impact bandwidth utilization if thousands of devices attempted to download them simultaneously. Meraki allows you to define these schedules at a granular level, balancing the requirement for up-to-date software against the impact on your network performance during core business hours. Monitoring the success of these installations is equally important, as the dashboard provides real-time metrics regarding deployment status for each individual device. If a device reports a failed installation, you can examine the specific reason in the logs, which might range from insufficient storage space to licensing shortfalls that require immediate investigation. Beyond basic installation, you can enforce specific behaviors using app-specific configuration settings, which are essential for secure enterprise environments. By leveraging managed app configuration, you can push parameters such as server URLs, authentication tokens, or restricted settings directly to an application during deployment. This ensures that users do not have to configure complex settings manually, and it prevents them from overriding those configuration choices. Furthermore, you can proactively block unauthorized software installations by utilizing Systems Manager restriction profiles, which can blacklist non-approved applications or prohibit access to consumer app stores entirely. When you remove a device from your management system or delete an application, the system handles the cleanup, ensuring that enterprise data associated with those applications is erased from the hardware. Establishing these automated workflows creates a resilient environment where compliance is the default state rather than an afterthought, ultimately securing your corporate assets against unauthorized software use. I will see you in the next lecture. Hi there. Let's explore how to enforce corporate compliance and security through device restrictions within the Meraki Systems Manager platform. In this session, we will focus on the technical implementation of hardware lockdown mechanisms and data protection policies. Managing mobile devices effectively requires moving beyond basic connectivity to enforcing strict security baselines across your fleet. When we talk about security restrictions in Systems Manager, we are essentially defining the boundary between corporate data and the underlying hardware capabilities. By centralizing these controls in the dashboard, we reduce the surface area for data exfiltration and unauthorized access. You should view these configurations as a form of governance that is continuously applied regardless of where the device is physically located. Without these granular controls, a device is merely a portal rather than a managed enterprise asset. We are aiming for a state where the hardware itself complies with your organization's internal security mandates automatically. One of the most critical aspects of this process is the ability to selectively disable hardware features that pose a risk to enterprise security. Modern mobile devices are sophisticated, often containing cameras, microphones, and the capability to mount external storage, all of which represent potential vectors for data leakage. Using payload configurations, you can push restrictions that programmatically toggle these features off when a device is under management. This is not about being restrictive for the sake of it, but about ensuring that corporate-issued assets adhere to your internal data handling policies. If a policy dictates that no physical media can be exported, simply disabling the ability to mount external volumes is far more effective than relying on end-user compliance. This implementation ensures that the policy follows the hardware, not the specific user interaction pattern. Beyond disabling hardware, maintaining data integrity requires mandatory encryption and robust authentication standards. When we configure passcode policies in the dashboard, we are defining the minimum acceptable entropy for device access. A strong passcode is the first line of defense, enforcing a complexity mandate, such as a minimum number of alphanumeric characters or the enforcement of special symbols, is a standard expectation in enterprise mobile management. Furthermore, enforcing file-level or disk-level encryption ensures that if a hardware unit is lost or stolen, the underlying data remains inaccessible to third parties. These policies are transparent to the user once deployed, provided they are communicated clearly, and they provide a uniform security posture across diverse operating systems. This consistency is vital in environments where you might be managing a mix of platforms under the same security umbrella. Automated compliance is perhaps the most powerful tool in your arsenal, moving management from reactive to proactive monitoring. You can set up specific triggers or remediation rules that take action the moment a device falls out of alignment with your corporate security policy. For example, if a user attempts to remove a mandatory work profile or disables a required security setting, Systems Manager can immediately trigger a containment action. This might involve revoking the corporate certificates that provide access to internal resources or moving the device into a restricted network sandbox. By doing this, you minimize the window of exposure, as the system does not wait for a human administrator to notice a security anomaly. It is, in essence, building a self-healing security perimeter that operates at machine speed. The final piece of this workflow involves the administrative response to these automated events through alerting. While remediation happens in the background, your security team needs visibility into the health of the entire endpoint fleet. Configuring thresholds for alerts ensures that you are notified when recurring violations occur, which might indicate a deeper issue with device hardware or user behavior. You are creating a loop where visibility and control work in tandem to provide a verifiable audit trail for compliance reporting. This capability is crucial for organizations that need to demonstrate security maturity to auditors, as you can prove that you have not only set a policy, but have the mechanisms in place to enforce it and respond when those mechanisms are challenged. Being able to document that managed devices are consistently restricted according to policy is a foundational requirement for any secure cloud management strategy. I look forward to discussing the next topic in our series during our upcoming meeting. Welcome back. In this chapter, we will explore the mechanisms of Systems Manager Sentry, focusing on how it integrates endpoint security posture with network access control. Systems Manager Sentry is a powerful framework that bridges the gap between endpoint management and network infrastructure, enabling dynamic policy enforcement. At a fundamental level, Sentry allows the Meraki dashboard, acting as the mobile device management platform, to communicate the trust state of a client device directly to the wireless access points and wired switches. When you enable Sentry, the network infrastructure stops treating devices as anonymous entities and starts treating them as verified participants that must prove their health status before gaining access to the network. This process relies on a secure handshake where the Meraki cloud informs the local hardware about the compliance status of a device based on its enrollment and security policy. If a device loses its MDM profile or violates a specific security constraint, such as having a disabled firewall or an outdated operating system, the infrastructure is notified immediately to change the access level or deny connectivity entirely. This automated enforcement reduces the burden on IT administrators by removing the need for manual port blocking or complex radius server configurations that often struggle with real-time updates. To deploy this architecture, you configure the Sentry policies within the Systems Manager section of the Meraki dashboard. You must define the specific conditions that trigger a change in access, which often involves an 802.x authentication flow using the Meraki cloud as the radius server or proxy. When an endpoint attempts to connect to an SSID or a switch port, the infrastructure performs a lookup against the Systems Manager database to verify the device's unique profile ID and its current compliance status. If the device meets the criteria, the network grants access through standard authentication mechanisms. But if it fails, the infrastructure can dynamically assign the device to a restricted VLAN or redirect it to a captive portal for remediation. This remediation path is critical because it provides a clear user experience for those who may have inadvertently drifted out of compliance, guiding them through the steps required to re-enroll or fix the specific configuration issues. The integration is seamless because the network hardware already inherently understands the Meraki Cloud's data structure, which eliminates many of the compatibility hurdles found in multi-vendor zero-trust deployments. One of the most robust aspects of Sentry is its ability to perform real-time posture checks, which addresses the inherent limitations of standard WPA2 or WPA3 security. Static passwords or certificates merely prove that a device is authorized to join the network, but they do not prove that the device is currently safe. Sentry fills this security vacuum. By utilizing the bidirectional communication between the Systems Manager agent on the client and the Meraki cloud, the network maintains a live record of health markers, such as the presence of encrypted storage, managed root certificates, or prohibited applications. Whenever an endpoint updates its status through the agent, the cloud pushes an instruction to the locally managed switches or access points to adjust the network access of that specific client. This means that a device disconnected from the internet or tampered with by a user will lose network access almost immediately, effectively isolating the threat before it can pivot to other resources. It is through these granular, automated checkpoints that we can truly enforce a least privilege access model at the edge, ensuring that data integrity is maintained regardless of whether the asset is a mobile handset or a corporate workstation. See you in the next session. Welcome back. In this lesson, we will focus on the technical mechanisms of device monitoring within the Meraki Systems Manager platform. Effective endpoint monitoring relies on the continuous telemetry data transmitted from managed devices to the Meraki cloud. When a device is enrolled, it establishes a persistent connection to the dashboard, which acts as the central clearinghouse for hardware and software inventory. You can retrieve granular data regarding the device model, operating system version, and serial number directly from the inventory view. This information is critical for auditing purposes, especially when you need to confirm whether a fleet is running the appropriate software versions to maintain organizational compliance. By tracking hardware inventory data, you avoid the administrative overhead of manual spreadsheets or legacy asset tracking tools. The dashboard aggregates this information into dynamic reports that update in real time as your environment changes. Consequently, understanding the structure of these data points allows you to build a proactive maintenance strategy rather than reacting to failures as they occur. Beyond basic hardware inventory, real-time location tracking provides necessary visibility into the physical distribution of your mobile and laptop assets. Systems Manager utilizes the GPS or Wi-Fi triangulation capabilities of the managed device to feed coordinate data back to the dashboard. You can translate these raw data points into actionable intelligence by configuring geofencing alerts. When a device boundary is defined, the engine monitors movement and triggers a notification if a device leaves a specified zone. This is particularly useful for detecting unauthorized asset movement, or ensuring that remote workers remain within authorized geographic regions. Monitoring these location events requires a stable reporting interval, which you can adjust manually within the device settings. While high-frequency reporting provides better accuracy for tracking, you must balance it against potential battery drainage on mobile endpoints. Operational health is another pillar of robust device management, specifically regarding battery health trends and connectivity logs. The dashboard provides a visual representation of battery degradation over time, allowing IT teams to identify devices that require hardware replacement before they become non-functional. Alongside this, the connectivity logs serve as an essential diagnostic tool for troubleshooting intermittent network access issues. You can examine logs to determine if a device failed to connect due to authentication timeouts, signal interference, or intermittent gateway reachability. These logs essentially act as the device's health record, which is indispensable when a user reports a persistent issue that occurs outside of your view. By correlating connectivity data with the device's uptime metrics, you can differentiate between local hardware faults and broader network-related outages. When remote troubleshooting becomes necessary, the Meraki dashboard integrates live tools that bypass the need for third-party remote desktop software. You can initiate a secure remote session to view the user's desktop, execute commands, or manage files directly through the Systems Manager interface. This capability significantly reduces the mean time to resolution by removing the barrier of complex connectivity setups or additional client software installations. Security is maintained because all interactive sessions are brokered through the encrypted cloud connection, ensuring that traffic remains contained within the management tunnel. As an administrator, you should prioritize these built-in tools to maintain a consistent support experience regardless of the user's location. Mastery of these monitoring and support features ensures that your entire endpoint fleet is both secure and performant, which is the primary objective of any enterprise management initiative. See you in the next lecture. Welcome to the segment On-Camera Deployment, where we will examine the architectural and configuration nuances of the Meraki MV line. In this chapter, you will master the principles of deploying smart security cameras that minimize bandwidth overhead while maximizing operational intelligence. Meraki MV cameras function through a hybrid cloud architecture, a design choice that fundamentally decouples video storage from video management. Unlike legacy systems that stream raw footage continuously to a centralized network video recorder or a cloud repository, these devices feature onboard solid-state storage. This means the high-definition video files remain hosted directly on the camera, effectively insulating your WAN from the constant traffic jitter and saturation traditionally associated with surveillance networks. The cloud dashboard serves solely as a control plane for configuration, user access, and metadata analysis, rather than a data silo for raw video packets. When you initiate a live view or retrieve a clip, the camera serves the request as needed, preserving your uplink capacity for critical business traffic. Before physical mounting, meticulous power planning is a mandatory prerequisite for a stable infrastructure. MV cameras are compliant with IEEE 802.3 AF and 802.38 standards for power over Ethernet, and your switch budget must account for this consumption, particularly when infrared illuminators or specialized heaters are active in outdoor models. Once powered, the initial onboarding process depends on reaching the Meraki cloud heartbeat over the local network. While wired connections are preferred for high-density environments, you may occasionally require wireless deployment profiles for specific architectural constraints. When you assign a wireless profile, the camera acts as a client on your existing Meraki wireless network, which requires that you have configured appropriate SSID settings and firewall rules to permit the device to reach the management plane without compromising the broader security posture of your wireless segment. Configuring the recording behavior of these devices requires balancing policy mandates with the limitations of onboard storage. You must explicitly set recording schedules, choosing between continuous recording or motion-based triggers, which significantly affects the total retention times achievable on the local disk. In many enterprise scenarios, motion-based recording is more efficient, as it indexes footage based on detected activity, allowing for rapid search and retrieval via the cloud interface. You should also consider the video quality settings, as adjusting the bitrate and frames per second directly influences the effective retention window of the integrated storage hardware. During this phase, you are also responsible for defining the user permission scope, ensuring that security personnel have access only to specific camera feeds that fall within their operational jurisdiction. Deployment efficiency also relies on understanding how the cameras interact with the broader Meraki ecosystem through metadata and cloud proxies. By offloading the compute-intensive tasks, such as object detection and motion analysis, to the onboard processor, the camera minimizes the data forwarded to the cloud to lightweight metadata packets. This hybrid model provides a scalable security network that remains performant, even as you grow your footprint from single-digit device counts to hundreds of units across distributed sites. When you follow these logical deployment workflows, you ensure that the physical security system acts as a seamless extension of your network fabric, rather than an unmanaged, bandwidth-heavy burden that triggers constant support tickets or performance degradation. By abstracting the storage layer, you unlock the ability to manage visual data with the same simplicity and policy-driven agility you apply to your switching and wireless infrastructure. See you in the next lecture. Welcome to this deep dive into Meraki video management, where we move past simple camera connectivity to true operational oversight. In this segment, we will explore the mechanics of organizing camera feeds and streamlining incident response workflows. Managing multiple camera feeds effectively requires a logical structure that transcends a simple list of devices. Within the Meraki dashboard, the video wall feature functions as a canvas for operators to drag and drop camera streams into specific layouts that match the physical floor plan of the site. By grouping cameras based on geographic locations or high-traffic zones, security teams can maintain situational awareness across an entire facility without toggling between multiple pages. Creating these groups is a matter of administrative organization, but the real benefit manifests when you share these views with specific personnel. Access control for video walls is managed through the dashboard, allowing you to grant granular permissions so that guards or facility managers see only the feeds dictated by their roles. This compartmentalization minimizes cognitive load during high-stress situations, ensuring that the relevant video is always center stage. When monitoring requires closer inspection, digital pan-tilt zoom, or DPTZ, allows users to zoom into specific areas of a high-resolution frame without moving a physical motor. This capability preserves the integrity of the total image while simultaneously allowing an operator to investigate suspicious activity in a controlled, non-destructive manner. The evidentiary value of surveillance video is only as high as the integrity of the export process, which is why Meraki includes built-in controls for handling footage. When an incident occurs and authorities or internal stakeholders require proof, you must be able to extract a precise temporal slice of the video without exposing unrelated sensitive data. The dashboard allows users to define a start and end time for a clip, which the system then encodes for secure download. During this process, you may find it necessary to apply privacy blurs over areas that are not relevant to the investigation or to comply with local privacy regulations regarding third parties. This feature is essentially a server-side processing task that ensures the exported file is compliant and ready for institutional use. Furthermore, each exported clip contains metadata that helps verify the file has not been altered since the moment of extraction, providing a chain of custody that is often mandatory in legal or disciplinary proceedings. By mastering these workflows, from organizing the wall to securing the export, you convert a passive recording system into an active, compliant, and highly efficient security operation. See you in the next lecture. Welcome to this dedicated session on maximizing the utility of your camera infrastructure through advanced analytic capabilities. In this chapter, we will explore how edge processing turns standard security video into actionable business intelligence. When we deploy Meraki MV cameras, we are rarely just interested in static recording for forensic purposes. Modern security demands more than simple archival. It necessitates the ability to efficiently parse hours of footage to find relevant events without manually scrubbing through timelines. By leveraging motion search, we define granular grids within the field of view to isolate activity to specific zones, such as a doorway or a merchandise display. When motion is detected within these designated areas, the system creates metadata that allows us to perform forensic searches in seconds rather than hours. This capability fundamentally changes the operational workflow from reactive monitoring to proactive incident resolution, ensuring that security teams remain focused on meaningful alerts rather than idle footage. Beyond manual search, motion recaps provide a synthesized view of visual activity over a specific time window. This feature aggregates snapshots of motion into a single image, effectively compressing the entire movement profile of a scene into a readable format. For instance, if you're monitoring a lobby entrance, a motion recap allows you to immediately visualize the flow of individuals throughout the day without watching a video stream. This level of abstraction is helpful for verifying that specific protocols, like opening hours or visitor screenings, were maintained according to policy. Relying on these recaps is a disciplined way to audit spatial security posture while reducing the time spent on routine verification tasks. We should also discuss the implementation of motion heat maps, which serve as a foundational tool for gathering business intelligence beyond pure security needs. A heat map tracks the density of movement within the camera's perspective, identifying areas where people congregate versus areas that see high transit but no occupancy. By analyzing this data, facilities managers can optimize the layout of a retail space, determine the placement of promotional signs, or identify bottlenecks in hallway traffic. The key here is the use of anonymized telemetry, which ensures that your analytical data remains privacy compliant while still providing the granular operational metrics required to improve facility efficiency. Advanced edge processing analytics also includes sophisticated object detection models that track person counts across physical spaces. Unlike traditional sensors that might be prone to false positives from non-human movement, the MV camera leverages onboard processing to distinguish humans from environmental noise. By configuring these detection parameters, an administrator can gather precise counts on how many people entered a building or accessed a restricted zone. This telemetry is transmitted back to the dashboard, where it can be used to monitor occupancy limits or evaluate the success of marketing campaigns. Because this detection happens at the edge, the reliance on continuous high-bandwidth streaming to a central server is mitigated, preserving your wide-area network performance. In optimizing these configurations, consistency is a virtue that you should prioritize across your entire deployment. If you set up detection zones on one camera, evaluate whether that same configuration logic should be applied to others to maintain a uniform standard of data collection. Inconsistent grid configurations lead to fragmented reporting, which makes it significantly harder to draw actionable conclusions when viewing the organization-wide analytics. You should also regularly review these settings as the physical environment changes, such as moving a chair or a display rack, which could unintentionally trigger false motion detections or obscure the view. Maintaining this discipline ensures that your edge analytics remain a reliable source of truth for both your security and operational stakeholders. See you in the next lecture. Welcome back. In this chapter, we explore how to configure and optimize retention settings on Meraki MV cameras to meet both operational requirements and regulatory storage mandates. Managing video surveillance infrastructure requires a deliberate balance between local storage capacity and the inherent need for long-term data preservation. When you deploy Meraki MV smart cameras, the default behavior typically emphasizes continuous recording. But this approach can quickly exhaust the solid-state storage within the camera if your retention needs are extensive. Your primary goal is to ensure that the footage remains available for the duration required by company policy, while optimizing the hardware constraints of the edge device. By adjusting the granularity of recording rules, you transition from a resource-heavy, always-on storage model to one that adapts to the actual activity occurring within the field of view. This shift effectively extends the retention period without necessitating the deployment of additional hardware or frequent manual interventions. One of the most effective mechanical levers at your disposal is the implementation of motion-based recording, which ensures that storage is consumed only when relevant activity is detected by the camera sensors. Within the dashboard, you can define specific motion zones to filter out noise, such as tree branches swaying in the wind or high-traffic areas that are irrelevant to security objectives. When you move beyond continuous recording to a motion threshold model, you drastically decrease the write cycles on the internal storage media while simultaneously increasing the effective archive duration. Furthermore, the ability to adjust the resolution and frame rate parameters provides a proportional reduction in data throughput, directly correlating to the number of days the camera can maintain local footage. It is essential to understand that lower resolutions or frame rates might be perfectly acceptable for broad surveillance, whereas critical entrances may demand the highest fidelity possible at the expense of storage depth. Beyond local storage, the platform offers the capability to configure cloud archives for specific time windows or event-based clips that require off-site redundancy. This is particularly significant when considering hardware failure or the physical theft of a camera, scenarios that would otherwise result in a total loss of local video evidence. By designating specific clips or scheduled intervals to be replicated into long-term cloud storage, you create a robust safety net that satisfies legal or insurance requirements for evidence preservation. These archives are managed centrally and do not rely on the health of the local edge storage, offering an independent recovery path. However, one must remain mindful of the bandwidth costs and the cloud storage capacity associated with high-resolution, long-term archiving, as these can accumulate rapidly across a large fleet of deployed devices. Compliance and privacy regulations often dictate that video data should not be held indefinitely, necessitating the use of structured retention policies that automate the deletion of aged footage. Manually managing bulk deletions is not only inefficient, but also prone to human error, which poses a significant liability risk in environments governed by strict data handling norms like GDPR or industry-specific privacy standards. By utilizing the dashboard to set explicit retention limits, you ensure that the system lifecycle for video data remains consistent with organizational governance. This automated pruning mechanism maintains storage health and mitigates the risk of exceeding local capacity, which could otherwise cause the camera to overwrite older data prematurely. Implementing these safeguards ensures that your surveillance infrastructure functions as a reliable, compliant, and predictable component of your broader enterprise environment. I will see you in our next session. Welcome to the chapter on sensor integration, where we will examine how environmental monitoring protects your physical infrastructure. We will cover the mechanics of connecting sensors to the Meraki cloud and aligning their data with your video surveillance streams. In this chapter, you will master the deployment of the Meraki MT sensor family, which is essential for maintaining the health of sensitive hardware environments. By integrating these sensors with existing wireless or imaging infrastructure, you gain a granular level of visibility that standard logging often misses. We will focus on the practical application of placing sensors to detect temperature spikes, humidity shifts, water ingress, and unauthorized door access. You will learn how to configure these devices to ensure they report data consistently, allowing for early intervention before minor facility issues escalate into catastrophic equipment failure. This is an indispensable skill for any network engineer tasked with maintaining data centers or remote edge locations where environmental stability is non-negotiable. Achieving proficiency here will move your management strategy beyond simple connectivity and into the realm of proactive facility guardianship. Successful sensor deployment relies on selecting the right gateway device, which acts as the bridge between the Bluetooth low-energy signals emitted by your sensors and the Meraki cloud backend. These gateways can be either MV smart cameras or MR access points, depending on your existing hardware footprint and the density of your facility. The gateway device must have an unobstructed line of sight or be within reasonable range of the sensors, as signal penetration can be significantly degraded by industrial racks, concrete walls, or heavy machinery. Once you pair a sensor with a gateway in the dashboard, the cloud handles the synchronization, allowing the sensor to report telemetry data without needing its own direct internet uplink. This architecture is efficient because it leverages existing power and network backhaul, reducing the need for additional wiring or specialized communication infrastructure. You should always conduct a site survey to identify the optimal location where your gateway can reliably collect sensor heartbeats while maintaining its primary function of wireless service or video recording. When positioning sensors, you must account for the specific environmental variables you intend to track, as placement often determines the utility of your logged data. For temperature and humidity monitoring, you should place sensors at multiple heights within a server rack, notably at the intake and exhaust points, to understand the thermal profile of the equipment. If you're monitoring for water leaks, sensors must be placed directly on the floor near cooling units or potential plumbing junctions where moisture is most likely to accumulate during a failure. Door access sensors consist of two pieces, and they must be aligned such that the internal magnetic circuit closes securely when the door sits flush in its frame. If the sensor is mounted on a metal door, you may need to use non-conductive spacers to prevent the metal surface from interfering with the magnetic field or the signal transmission. These small, practical details are what differentiate a functional, reliable environmental monitoring system from one that generates false positives or disappears from your dashboard intermittently. Integrating sensor data with visual context from your MV cameras provides an incredibly powerful diagnostic tool for your operations team. Inside the Meraki dashboard, you can define sensor thresholds that, when breached, trigger the system to bookmark video footage from the nearby camera at that specific timestamp. Imagine receiving a notification that a room door has opened after hours, and instead of just seeing a text alert, you can click on that alert to watch the video of who entered the room. This direct correlation between cold, numeric environmental data and visual evidence is the core advantage of the Meraki ecosystem's tight integration. You can visually verify if a temperature spike was caused by a legitimate cooling unit malfunction or simply by a technician leaving a server rack door propped open for maintenance. Aligning these data streams allows for rapid incident resolution and significantly reduces the mean time to repair for issues that would otherwise require a physical site visit to investigate. Maintaining physical visibility over your operational areas requires that you configure robust alerting directly within the dashboard based on the telemetry gathered by the sensors. You must create thresholds that are sensitive enough to capture real issues without overwhelming your staff with noise from minor, transient fluctuations that do not indicate a problem. For example, a temperature sensor should be configured to alert only when the value stays above a critical threshold for a sustained period, avoiding alerts during a momentary opening of a door. You should also utilize the reporting features to perform trend analysis, which can help reveal slow developing issues like the gradual fatigue of a climate control system. By observing these trends, you can transition your infrastructure management from reactive firefighting to predictive maintenance, effectively saving your hardware from environmental stress. This granular control is only possible when you treat your environment as a manageable part of your network rather than a secondary concern. See you in the next lecture. Welcome back. In this chapter, we will explore the orchestration of automated responses to physical security and environmental threats within the Meraki platform. Meraki Smart Alerts transform raw data from cameras and sensors into actionable intelligence that drives operational efficiency. By linking physical analytics like motion detection to proactive notification channels, you shift your infrastructure management from a reactive posture to one of real-time intervention. This capability is essential for any deployment where hardware uptime and site security are critical performance indicators. Throughout this chapter, we will master the logic required to build resilient alert pipelines that scale across your entire enterprise. You will learn to integrate these environmental inputs with your existing communication stacks, ensuring that your support systems remain informed without being overwhelmed. Configuring alerts effectively requires a deep understanding of threshold management and delivery logic to avoid the common pitfall of alert fatigue. When managing environmental sensors, such as those monitoring temperature or humidity in a server closet, you must define specific upper and lower bounds that trigger an event. These thresholds should reflect the actual tolerance of your hardware, meaning a setting that triggers a warning at 30 degrees Celsius might be appropriate for a general office, but a critical alert at 25 degrees is safer for a high-density data cabinet. Beyond setting the trip point, you must also consider the reporting interval to ensure that transient spikes in temperature do not generate a constant stream of unnecessary notifications. This nuance is precisely what distinguishes a well-tuned monitoring system from one that administrators eventually learn to ignore or disable. Motion-based alerts function differently because they rely on the logic of person detection and spatial boundaries rather than constant data streaming. You define these parameters in the camera settings by designating specific restricted zones that should be cleared during off hours. A motion alert effectively acts as a Boolean gate. When the combination of a time-based schedule and a visual object trigger is true, the system fires an event. This workflow allows security teams to monitor physical entry points or sensitive equipment areas without requiring a manned monitor. By applying these constraints thoughtfully, you ensure that the system only alerts during hours when activity is statistically anomalous, which significantly reduces false positives while preserving the integrity of the secured area. Connecting these events to modern notification destinations requires an understanding of how the Meraki dashboard facilitates external communication via webhooks. By directing the output of a sensor event to an HTTP post destination, you can feed triggers directly into platforms like WebEx, Slack, or automated incident management systems. When an environmental threshold is breached, the webhook carries the event payload to an application listener, which can then parse the JSON data to initiate a response workflow. This integration is modular, meaning you can direct different alert severities to different communication channels or escalation groups. Implementing this level of automation turns your network infrastructure into a self-reporting ecosystem capable of triggering digital support tickets based on physical world occurrences. Managing the frequency of these alerts involves configuring notification throttle filters, which serve as a necessary dampener on the notification pipeline. Without throttling, a rapid, recurring event could potentially flood your chat channels and distract team members from other critical tasks. You should configure these dampeners to group similar alerts into a single summary notification if the frequency exceeds a defined count within a short window. This systematic approach ensures that you receive only the most relevant notifications while maintaining a historical audit trail within the dashboard logs. Establishing these filters is a balancing act between sensitivity and usability, requiring iterative testing to find the optimal window for your unique environment. Building effective escalation workflows is the final step in ensuring that critical facility events are resolved by the right personnel. You can configure the notification engine to send initial alerts to a primary monitoring team and only escalate to senior engineers if the condition persists beyond a specific duration. This tiered structure respects the professional time of your team and ensures that high-priority issues receive priority handling. By automating these workflows, you reduce the time to resolution for physical infrastructure threats like overheating hardware or unauthorized access. These automated pipelines are a core competency for any engineer tasked with maintaining the availability of large-scale, distributed Meraki deployments. I will see you in our next session. Welcome back. It is time to explore the operational utilities available within the Meraki dashboard. We will examine how to leverage these live diagnostic tools to effectively isolate and resolve infrastructure issues without requiring physical access to the hardware. The suite of live tools integrated into the Meraki dashboard serves as a primary mechanism for reducing mean time to resolution by eliminating the need for on-site troubleshooting visits. When a network issue occurs, you should begin your investigation by navigating directly to the affected device in the dashboard. From the main status page, you can access the Tools tab to perform low-level network verification tasks. You have the ability to run standard connectivity tests such as ping to verify reachability between a device and target hosts on the local network or the internet. Similarly, the traceroute function allows you to identify the specific hop where a connection might be failing, which is essential for diagnosing routing anomalies or upstream connectivity disruptions. These utilities are executed directly from the cloud, meaning they reflect the network state from the perspective of the Meraki hardware rather than your own client device. Physical layer validation is often overlooked, yet the dashboard provides internal cable testing capabilities for MS switches to identify damaged copper cabling or incorrect wiring standards. If a port is reporting errors or failing to negotiate the expected link speed, you can trigger a cable test to receive an immediate report on the approximate distance to a fault or the status of individual wire pairs. Beyond cabling, managing power delivery for connected devices is equally straightforward with real-time power monitoring. You can observe the exact wattage draw on a switch port to ensure a connected access point or camera is receiving sufficient power within the budget defined by its power class. If a port stops responding, the toolset allows you to cycle the power of that specific interface, which is functionally equivalent to unplugging and replugging a cable, often resolving hang-ups in legacy client devices. Packet capture represents perhaps the most powerful investigative tool at your disposal, allowing you to intercept traffic directly at the device interface level. You can configure filters to target specific source or destination MAC addresses and IP addresses to streamline your analysis and avoid capturing irrelevant data. Once initiated, the dashboard provides a mechanism to download the capture file in PCFP format, which is directly compatible with protocol analyzers like Wireshark. This cloud-based packet capture avoids the complexity of setting up port mirroring on physical switches and allows for visibility even when you are thousands of miles away from the hardware. It is important to remember that these captures can be run on specific physical ports of a switch or on the uplink and wireless interfaces of a Meraki access point, providing full horizontal visibility across your network infrastructure. When facing more drastic scenarios like a device becoming unresponsive to management traffic, The Meraki platform offers recovery options that do not always necessitate a full factory reset. Appliances can be rebooted remotely from the dashboard at any time, which helps clear transient software-related errors that might be impacting throughput or control plane stability. In the event of a total WAN failure, if you are physically present at the site, you can utilize the local status page to gain visibility into the appliance even when cloud connectivity is severed. This local interface provides diagnostic information regarding the current upstream status, local IP assignment, and potential DNS resolution issues that might be preventing the device from establishing its secure tunnel to the Meraki cloud controllers. Integrating these distinct tools into your daily support workflow ensures that you are consistently making data-driven decisions when configuring or maintaining your network. I will see you in our next session. Welcome back to our exploration of network operations, where we today turn our attention to the robust alerting infrastructure intrinsic to the Meraki ecosystem. In this chapter, we are going to navigate the complexities of building a resilient monitoring stack that proactively surfaces network health issues and anomalies. We will refine how you configure alerting profiles and orchestrate external integrations to ensure that visibility is not merely a reactive byproduct of a failure, but a continuous stream of actionable telemetry. Effective monitoring begins with foundational alert configuration, where the Meraki dashboard acts as the central nervous system for your global infrastructure. When you navigate to the alert settings within the organization or network scope, the platform provides granular control over thresholds for device connectivity, uplink status, and configuration changes. Configuring global email alerts for device offline events serves as your primary line of defense, allowing administrators to respond to localized power failures or ISP outages before they escalate into service-impacting incidents. You must define a clear escalation path, ensuring that alerts are routed to the appropriate operational groups based on the severity of the event. It is also equally critical to suppress redundant notifications to avoid the inevitable trap of alert fatigue, which often leads teams to ignore genuine systemic failures. Beyond visual dashboard indicators, integrating external syslog servers is indispensable for maintaining a long-term audit trail and meeting stringent compliance mandates. When you point your Meraki devices toward a dedicated syslog aggregator, you effectively offload the storage of operational logs from the transient cloud memory to your persistent infrastructure. This allows for cross-platform log correlation, where you can correlate event logs describing client connection behaviors with broader performance metrics. By analyzing these logs, you can reconstruct the sequence of events leading up to a specific user authentication failure or an unusual traffic spike. Centralized log management turns raw, ephemeral data into a searchable historical database, which becomes our most valuable asset during deep dive forensics or security audits. SNMP monitoring agents remain a vital component of traditional network management stacks, and Meraki supports this deployment through the configuration of communities and trap destinations within the dashboard. While the cloud interface provides superior visualization, SNMP allows you to integrate your Meraki hardware into legacy, monitoring, and management platforms, ensuring a unified view across multi-vendor environments. You should carefully select the metrics you intend to poll, as frequent polling of a large device estate can introduce unnecessary chatter on the management plane. By setting up SNMP traps, the devices can push asynchronous notifications of hardware status changes directly to your management server instantly. This hybrid approach to monitoring provides the flexibility needed to maintain consistent visibility protocols regardless of whether the hardware follows a cloud-native or traditional management model. Change logs provide an immutable history of administrative actions, which is essential for network governance and troubleshooting misconfigurations. Whenever a dashboard administrator modifies a firewall rule, updates a VLAN interface, or shifts an SSID configuration, the system records the actor, the timestamp, and the specific property changes. Regularly reviewing these audit trails helps clarify whether a performance degradation was caused by an external environmental factor or an internal oversight during a maintenance window. Interpreting event logs in conjunction with these change logs allows you to establish a causal relationship between configuration intent and network behavior. This disciplined approach to tracking modifications acts as a safeguard, enabling you to revert to a known good state if a recent change negatively impacts the quality of service for your end users. NetFlow configuration provides the granular visibility needed to understand traffic patterns and capacity utilization across your wired switching infrastructure. By exporting traffic flows to an external collector, you gain insights into the conversation dynamics between clients, servers, and external internet destinations. This level of traffic analysis is critical for identifying potential bandwidth bottlenecks or detecting anomalous data transfers that might indicate a breach or a misconfigured service. Understanding the flow of data across the network core allows you to make informed decisions about bandwidth allocation and policy enforcement, effectively keeping your network optimized under changing demand. Combining NetFlow data with the operational logs previously discussed creates a high-fidelity monitoring baseline that alerts you to early performance degradation before it impacts the business. See you in our next technical deep dive. Welcome to this exploration of the Meraki Dashboard API. In this chapter, we will master the programmatic control of your infrastructure to transition from manual clicks to scalable automation. The Meraki Dashboard API is a powerful RESTful interface that allows administrators to interact with their network infrastructure programmatically. By treating your network as code, you move away from the limitations of the graphical user interface, which is ideal if you manage multiple organizations or thousands of individual devices. To begin, you must enable the API within the organization's settings of the dashboard and generate a unique API key. This key acts as your credential, and it must be included in the header of every HTTP request you send to the Meraki cloud. It is important to treat this key as a sensitive password because it provides full access to your organization's configuration data. Once enabled, you can start making requests using standard REST methods like GET, POST, PUT, and DELETE to read or modify your network environment. Understanding how these REST methods map to dashboard actions is foundational to your success as a Meraki engineer. A GET request is essentially a read-only operation that allows you to pull configuration details, device statuses, or telemetry data into your own analysis tools. When you need to change settings, such as updating an SSID configuration or modifying firewall rules across hundreds of networks, you will utilize PUT or POST requests. These requests carry data in JSON format, which is a lightweight, human-readable structure that facilitates the exchange of complex nested data. You must ensure your JSON is properly formatted, as even a stray comma or an improperly nested bracket will cause the API to reject the request with a syntax error. Most programming languages, including Python, have native libraries to handle this serialization, which makes building robust automation scripts significantly easier. The real power of the API becomes apparent when you consider use cases like mass provisioning or automated reporting. Imagine you need to deploy a new security policy across 50 geographically dispersed sites. Instead of visiting 50 separate dashboard pages, a single script can push these changes to all of them in seconds. You can also automate the extraction of telemetry data, such as port usage statistics or client signal strength, which can be sent to an external data warehouse for long-term trend analysis. This approach not only ensures consistency across your entire environment, but also eliminates the human error associated with repetitive data entry. Furthermore, by integrating these API calls into your existing IT orchestration systems, you create a unified management plane that bridges the gap between your network, server, and endpoint management. Moving beyond manual GUI workflows helps you scale your operations effectively while maintaining precise control over your documentation and security posture. See you in the next lecture. Welcome back, and today we are shifting our focus to managing the firmware lifecycle for your Cisco Meraki infrastructure. This topic is critical for maintaining long-term stability and security within your network environment. In any enterprise network, firmware management is not merely a task of clicking update buttons, but a strategy for risk mitigation. The Meraki dashboard provides a centralized mechanism to oversee the firmware health of your entire fleet, from wireless access points to security appliances and switches. Rather than treating updates as arbitrary chores, you should view them as essential maintenance that addresses security vulnerabilities and improves hardware performance. Because the Meraki cloud handles the heavy lifting of orchestration, your primary responsibility becomes the implementation of a sane, staged release strategy. This prevents unexpected downtime during peak hours and ensures that your production environment remains predictable throughout the lifecycle of the hardware. By applying a systematic approach to these updates, you minimize the blast radius of potential bugs while staying compliant with necessary security standards. The most effective way to manage these updates is through the implementation of firmware staging groups. Instead of pushing updates to every device in your organization simultaneously, you define specific groups of devices or sites that receive early updates. This allows you to validate new code against a handful of deployments that represent your broader network architecture. If you encounter issues during this pilot phase, you can halt the rollout before it impacts your core business operations. Within the dashboard, you navigate to the firmware upgrade settings to categorize your sites or tags, which is where you orchestrate these staging windows. A well-configured staging group acts as a circuit breaker, providing you with the necessary insight to assess stability before the rest of your infrastructure follows suit. Configuring automatic update windows is another essential component of this lifecycle, as it removes the manual toil of initiating deployments after hours. When you define these windows, you specify exactly when the controller is permitted to perform a reboot of the hardware, ensuring the update process happens during low-traffic periods. You should always align these windows with your organization's maintenance schedule to prevent any overlap with sensitive workflows. This automation is particularly useful in large-scale deployments where manual intervention for every site would be logistically impossible. However, automation does not imply a lack of oversight, as you must remain diligent in reviewing release notes provided by Cisco before scheduling your windows. These notes document critical security patches and known issues that dictate when an update is mandatory and when it might be prudent to wait for a subsequent minor release. For environments that require strict regulatory compliance, the Meraki firmware lock feature provides an additional layer of control. By engaging a firmware lock, you prevent the cloud controller from automatically upgrading a specific device or network to a newer version. This is invaluable when you have validated a specific release against internal compliance requirements or third-party audit standards. Because you explicitly define which version the hardware should run, you retain complete authority over the platform's lifecycle, ensuring that stability is never compromised by an unwanted update. If you discover a critical vulnerability is patched in a later version while a lock is in place, you must perform a deliberate manual process to unlock the device and promote it to the required software version. This manual gatekeeping reinforces your command over the network behavior and prevents drift across your fleet. Should you ever find yourself in a situation where a new firmware version introduces unexpected regressions, the recovery process is equally vital. Meraki allows for manual rollbacks in specific scenarios, though one should aim to avoid reliance on this by conducting thorough validation and staging. When you do encounter an issue, it is important to communicate with support to document the behavior before attempting a rollback, as this helps prevent similar issues in future versions. A rollback is essentially reverting the device to its previous, known good firmware state, which is why maintaining visibility into your current software versions is non-negotiable. Your goal is to treat firmware not as a static component of the hardware, but as a dynamic, versioned entity that requires constant attention. By establishing these structured lifecycle workflows, you transform your network from a reactive bundle of hardware into a resilient, managed system that evolves securely. I will see you in the next lecture. Welcome to the chapter on Network Insight. Here, we will explore how to transition from reactive troubleshooting to proactive application performance management using Meraki tools. Meraki Insight provides a specialized layer of observability that differentiates itself from standard monitoring by shifting the focus from infrastructure status to application experience. While traditional network management platforms often report on link uptime, packet loss, or interface throughput, they frequently fail to answer the most critical question regarding user experience. Is the service performing as expected? Meraki Insight addresses this by correlating WAN connectivity metrics directly with application throughput and response times, allowing for a clearer understanding of how the network impacts cloud-delivered services. This functionality is particularly vital in modern environments where traffic is predominantly destined for SaaS applications, rendering traditional perimeter-based monitoring insufficient for ensuring consistent performance. By collecting flow-level data directly from the security appliance, the solution constructs a comprehensive view of the transaction path from the client to the server, providing the granular visibility necessary to isolate performance bottlenecks across complex distributed networks. To leverage this effectively, you must first understand how to establish meaningful baselines for your critical web applications. The platform automatically identifies and categorizes traffic, but it relies on your input to determine which applications represent the core of your business activity. Once an application is enabled for monitoring, the system begins a period of data collection to observe its characteristic behavior, including round-trip times and server response behavior. This baseline serves as the reference point for all subsequent performance analysis, enabling the system to trigger alerts when current performance metrics deviate significantly from historical norms. It is important to remember that these baselines are dynamic, and you should ensure that your monitoring profile reflects actual usage patterns to avoid false negatives or irrelevant alerts. By effectively setting these parameters, you enable the dashboard to provide proactive notifications rather than simply recording failures after they occur. When analyzing performance drops, the WAN Insights dashboard offers a structured approach to fault isolation that eliminates much of the guesswork associated with ticket triage. You are presented with a waterfall view that breaks down the total application response time into its constituent parts: network latency, server response time, and application processing time. If an application exhibits poor performance, you can instantly observe whether the delay originates in the client's local access network, the intermediate ISP transport path, or the SaaS application provider itself. For example, if you see high network latency coupled with packet loss, the issue is likely tied to the wide area network or the ISP connection. Conversely, if the network metrics are optimal but server response times remain high, the problem is almost certainly contained within the cloud application service, which effectively empowers you to engage the correct support team without unnecessary internal finger pointing. Beyond mere diagnosis, Meraki Insight provides predictive capabilities that can be utilized to optimize traffic paths, particularly in environments utilizing multiple ISP uplinks. The dashboard analyzes traffic patterns across your WAN links and provides recommendations for path steering policies that prioritize stable, low-latency connections for critical SaaS applications. You can interpret these insights to adjust traffic shaping or SD-WAN policies, ensuring that sensitive applications are always routed through the most efficient path available at any given moment. This transformation from analyzing historical logs to implementing data-driven routing decisions is the core of modern network optimization. By treating the network as an enabler of application performance rather than just a pipe, you build a significantly more resilient architecture. Utilizing these tools allows you to maintain high performance in a cloud-centric enterprise where user satisfaction is directly tied to the speed and reliability of web-based tools. I will catch you in the next one. Welcome. Let us discuss how to effectively interact with Cisco Meraki support and manage the administrative lifecycle of your hardware. This chapter focuses on professionalizing your interaction with vendor services to ensure rapid resolution of complex issues and clear hardware replacement paths. When a technical issue exceeds the capability of your in-house diagnostics, the efficiency of your support request becomes the primary variable in resolution time. The foundation of a productive support relationship lies in the quality of the information you provide at the moment of case creation. Before reaching out, you should always gather diagnostic logs and packet captures from the Meraki dashboard, as these artifacts are the first things a support engineer will demand. You must also leverage the integrated case management portal within the dashboard, which links your specific organization's identity directly to the support request. By granting access to the support team through the dashboard's secure administrative delegation feature, you eliminate the need for back-and-forth communication regarding account permissions. This specific workflow ensures that the engineer can view the network state, configuration, and event logs exactly as you see them, which significantly reduces the time spent on manual problem replication. Consistency in report documentation, including timestamps, device serial numbers, and a clear description of the impact, allows Tier 2 or Tier 3 support teams to bypass the standard initial triage steps. Providing a coherent narrative of the issue, combined with direct read-only access to your organization, creates a high-fidelity environment for troubleshooting. Escalation is not merely a mechanism for expressing frustration, but a structured process for when a case does not progress within the established service-level agreements. Understanding the Meraki escalation path requires recognizing when a technical hurdle has transformed into a business-critical outage that threatens core infrastructure availability. You should utilize the case portal to track ticket progress and communicate directly with active engineers before considering formal escalation. If the severity level of your case needs to be adjusted, documented business impact metrics, such as the number of affected users or functional downtime, must be clearly articulated to the support lead. This clarity ensures that the escalation request is grounded in operational facts rather than subjective urgency. When you manage these interactions with technical precision, you transform the vendor support team into an extension of your own department. Maintaining this disciplined approach to documentation and communication is exactly what separates competent network administrators from those who struggle to maintain enterprise-grade uptime. Hardware lifecycle management is the secondary component of our support workflow, particularly regarding the advanced replacement policy. Meraki provides a limited lifetime warranty for most hardware, which includes the replacement of defective units to minimize prolonged network disruption. You must familiarize yourself with the difference between a standard return merchandise authorization and the expedited advanced replacement process, as the latter is designed to get a replacement unit into your hands before the faulty item is returned. Initiating these workflows requires accurate record-keeping of your hardware serial numbers and their association with the current organization and network. Should an unexpected hardware failure occur, having the device registered correctly in the dashboard allows support to verify warranty status instantly without administrative delay. Your ability to provide the correct shipping address and verify the physical condition of the hardware ensures that the logistics side of the replacement process proceeds without unnecessary hurdles. Managing these assets effectively within the dashboard is not just about inventory control, but about ensuring that your support contract remains a functional insurance policy for your production environment. See you in the next lecture. We have reached the end of our journey, and it is time to consolidate the knowledge you have acquired throughout this course. We will now review the fundamental pillars of the Meraki architecture to ensure you are fully prepared for the certification exam. The architecture of Meraki relies fundamentally on the out-of-band management model, where the control plane resides securely in the cloud, separate from the user data plane. When you troubleshoot, remember that your configuration changes push from the dashboard directly to the devices via a persistent, encrypted tunnel. This design choice ensures that even if you lose connectivity to the cloud, your local switching, routing, and wireless traffic continue to flow without interruption. You have learned that the organization and network hierarchy is the backbone of your deployment, necessitating a logical structure for effective management. Proper administrative access control, utilizing role-based organization-level permissions, is critical for maintaining an audit trail and ensuring least privilege security across the enterprise. Mastering the dashboard navigation and understanding the nuances of the licensing model will prevent unexpected service disruptions and help you maintain operational continuity. Wireless optimization requires a deep understanding of RF behavior and the intelligent implementation of SSID security settings. We discussed how access point placement, combined with dynamic channel assignment and transmit power control, creates a stable environment for high-density traffic. When configuring guest networks or implementing WPA3, always prioritize the balance between user convenience and robust security policies. Your focus should remain on the health of the RF spectrum, where tools like location analytics and Meraki Insight provide the visibility needed to make informed optimization decisions. Remember that Layer 3 switching is not just about connectivity, it is about proper VLAN segmentation, efficient spanning tree configuration, and granular quality of service prioritization for business-critical applications. By stacking your access switches correctly and enforcing strict port policies, you establish a resilient foundation that supports the throughput demands of a modern enterprise environment. Security and SD-WAN capabilities allow for complex traffic steering and robust threat protection across distributed sites. The strength of the Meraki MX appliance lies in its ability to simplify site-to-site VPN connectivity through intelligent auto-provisioning while maintaining strict control over firewall rules and content filtering. When analyzing scenarios for the exam, consider how traffic shaping policies and SD-WAN steering rules affect the user experience during path failover events. The integration of Systems Manager for mobile device management acts as an extension of this security perimeter by enforcing compliance profiles and security restrictions. Because threat protection and security appliances operate in tandem with your network infrastructure, you must master the correlation between endpoint health and network access. This holistic view of the stack is what defines a true Meraki solution specialist. Finally, your troubleshooting methodology should always rely on the live tools provided within the dashboard ecosystem. From utilizing the network topology map to examining individual client events and leveraging the Meraki dashboard API for automation, you have the data needed to isolate issues quickly. Firmware lifecycle management is another critical operational task that must be planned carefully to avoid downtime and ensure the availability of the latest security patches. Pay close attention to alert infrastructure, as these real-time notifications are your first line of defense when something deviates from the established baseline. By synthesizing these operational strategies with your technical understanding of the hardware, you are now equipped to manage complex, full-stack enterprise deployments with confidence. You have the tools, the logic, and the understanding necessary to approach the exam with clarity and focus. I wish you the best of luck with your upcoming certification attempt. See you soon.